Good morning, everyone. Welcome back. So we start the second day of the school. Remember that yesterday we mentioned that the focus of today is interfaces, more and twistronics. Leni and Nini will be the lecturers. And yeah, that's it. So we start with the first one that Janendra from ICMAB will share the session. Thank you. Pero pasa también. Sí, te hace todo. Y el láser cuando lo aprietas son 2 segundos y te aparece.
Good morning, everyone. Welcome to the second day of this school on 2D materials. So we are privileged to introduce you our new speaker, Dr. Leni Bascones. She is a theoretical physicist from Institute of Material Science of Madrid. She has done her PhD in the University of Autónoma Madrid, and then she moved to University of Texas for her first postdoc, and the second postdoc is done in ETH Zurich. So her main expertise in electronic properties of quantum materials. So during the first year of her career, she studied the transport properties of mesoscopic systems such as nanocontacts, Coulomb blockage physics. And after that, during her postdoc in Zurich, she specialized in correlated materials, trying to understand both the nature of correlated systems and their signature in different experiments. She worked first in high TC cuprates and later in iron-based superconductors, also Hwang metal physics. So in the last few years, she dedicated her research in the field of graphene Moire systems, particularly twisted bilayer graphene. So welcome, Dr. Leni, and the floor is yours. Just one comment. The online audience, please put your question in the chat line. And the live audience, actually, feel free to ask any question. You just raise your hand and I'll give you the mic. Okay.
Okay. First of all, thank you very much for the invitation. I'm very happy to be here. It's also my first time here at ICMAB, so it's good to know our brother institutes. I'm going to give a general introduction to some of the states and some of the systems that have been studied with this twisting strategy, or also other ways to get more materials. This is going to be different to the talks. Yesterday is going to be more focused on also on electronic states that we can observe. So not on the synthesis or preparation of these systems. Okay. So as you know, so a couple of decades ago, so there was the exfoliation of the isolation of graphene, and after that of many other materials, and so people start dreaming on having these materials prepared a la carta, stacking different type of 2D systems. But there is another degree of freedom, which is the possibility to play with the stacking of these systems, like you see here in a twist heterostructure. So what you can see here, the first thing is that in this twist heterostructure, so what it calls the attention is this pattern, this Moire pattern, that is going to give us a new unit cell in our system, the Moire unit cell. You can see here how if we have two lattices and we rotate them, depending on the angle in which these lattices are rotated, the periodicity is going to change. And so this Moire unit cell is going to have a different size, and also the pattern is going to change in some way. Now, this new periodicity in the system can become very large. So it's larger as the angle becomes smaller, and in particular, for small angles like the ones I'm going to discuss, in this talk, like 1 degree, the lattice constant is around 13 nanometers. So this means that in the unit cell, there are more than 10,000 atoms. So it's a completely new different world as compared to the material, the bulk materials, or even the 2D material that has been mostly studied. So what you can see here when there is this twisting is that, well, there is an alternation on the way in this Moire pattern on how the 2 layers see each other. And in particular here, so here at the center of this Moire unit cell, the stacking is close to an AA stacking, in which you have the atoms on top of the atoms of the 2 layers. And then here at the vertices, so it's closer to what is called in the graphene, the AB stacking, so in which, well, the 2 layers are shifted. So, well, people have observed that there were like stacking defects on the surface of some materials, and in particular graphite. But in 2010, so Evan Ray, so before the main interest has been on the structural properties. What Evan Ray did was to say, okay, so how does the band structure, how do the density of a state changes when we look, when we change the angle? So, well, she did STM experiments, and so they look at the different stacking angles, twist angles. So what they were doing is they were in the system, they were identifying the angle from the periodicity of the Moire pattern that they saw. These Moire lattices. So this is, you see here, this is nanometers. No, this is, in fact, yeah, well, is that this is a large angle. And what she saw is that, so when she was changing the angle, this is the DIDB, which is giving us the density of states effectively. And so you can see that these 2 peaks, which are band of singularity, so they are like, there is a lot of density of states. So they became much closer and closer when this angle was made smaller. And interestingly, when the angle was around 1.1 degree, more or less 1.16, so they were really, really close. So they were like 12 millielectron volts close to each other. So this was telling us that it was suggesting that the system had very, very flat bands for this twist angle. So what is important here, and later we will see, is that if we have flat bands which are, so if we have bands which are very flat, so the width of the band is giving us information on the kinetic energy of the electrons. So if the bands are very flat, that means that the electrons have small kinetic energy. So the interactions are going to have a very strong effect and can give rise to new states. Well, well, people studied how were the bands of this system theoretically. So you see here, well, the first thing that you see here is an spaghetti of bands. And this is because, well, we have this very large Moire unit cell. So this means that when we go to momentum space, so the Moire unit cell is folded. And so we have, so this was one Brillanson of graphene. This is the other one that is rotated, these big ones. These are the graphene Brillanson, but then the Moire Brillanson it's much, much smaller. So we have all this folding, okay? So I'm going to focus on the bands that are close to the Fermi level, to the chemical potential, and you can see how when you change the angle, around 0 here in this case, around 1.0 degrees, there is this very, very flat band, okay? So this is what is going to interest to us, because it's what I say. The people said, okay, this system has to be interesting. What they saw in this paper is that there is not just one angle at which the bands become so flat, but this is just the largest angle, but there are some other angles at which this also happens. So there are several angles. So this is called a magic angle. Magic angle is when the bands become. And this is very, for the graphene system, just for the twist bilayer, this is very, very, so you cannot move much from this angle. It's like just changing the angle 0.1 degree, it makes the band much wider. Well, of course, the boom of twistronics came, so it started a few years ago. What Pablo Jarillo did, it was, well, now he had really a twist by layer. It was much more controlled. So he had 2 layers of graphene really rotated around 1 degree. And so he put already in 2016, he had put this twist by layer in a gate structure. And the interesting thing here is that with these gates, he is able to dope the system. Normally, when we work with a bulk material, if you want to dope the system, you have to do a chemical substitution, okay? And if you try to dope with a gate, so the amount of electrons that you can add in general to a system, it's very, very small. What is new here is that because this unit cell is so large, even if you add the number of electrons that you add are very few, you really, so in total, even if the density is small, so you can really dope several electrons or several holes per unit cell, okay? So somehow, well, these are these flat bands of the magic angle twist by layer graphene. So they can hold up to 4 electrons or 4 holes. And here the degeneracy is because we have 2 valleys. So one that comes from the K and one that comes from the K prime point of the graphene. So then we can, these ones, we can have up to 4 electrons or 4 holes. Now, you can see here, this state is expected to be metallic up to filling 4 or up to filling -4, right? Because we have a band that is crossing the Fermi level. What Pablo saw is that, well, you have this insulating state. This is this is -4. This is in 10 to the 12, but this is -4. This is +4. Not this one. This is +4. So that's okay. But the new thing is that he saw that when he had -2 and 2, the feeling was -2 and 2, that you expect that the system is metallic, he found insulators. So what this is telling us is that these insulating states are really caused by the electronic correlation. And he also found a surprise, even more. Well, that was already quite a surprise, but the other surprise is that, well, there was a superconductivity very close to these insulated states. So, well, this was really an amazing. I don't know if you were, so he presented that at the March meeting 2018. I don't know if any of you were there, but that was a really shocking day. So, so here there are many things that were interesting. So of course, well, there were these insulated states. There was the superconductivity that was a big thing there. And so one thing is that if you realize and how, so here you have insulating states or resistive states for this specific case, even if they call it insulated. And you have the superconductivity, and in reality, the amount the tune going from the insulated to the superconducting state just really adding 1 electron per something like 100,000 atoms. That really so extremely sensitive. This is so this is one of the amazing properties. Of course, it's also called a lot the attention that this phase diagram resembles the one of cuprates. So somehow the idea is like, can we really understand finally the cuprates? Well, already after this experiment, so twistronic was considered the most important discovery that year in physics in 2018. But well, at that time, people even couldn't dream how impressive has been the advancement in this field, because many more things have appeared after that. Well, one thing is not going to go in detail, is that really the phase diagram of twist by layer graphene is much richer. Later I will show some of the states. it's much richer than Pablo saw in the first paper. So there are samples in which you have seen several superconducting domes. For example, there are more correlated insulating states. People have observed a lot of different type of broken symmetry states. There are fascinating reorganization of the spectral weight changes of the density of a state as a function of doping that are called cascades. And there is also a region in which the resistivity depends linearly on temperature, that is telling us that our system is interesting in terms of what the correlations are doing, and which in fact also this type of properties are seen in the Cooper. So what this has been really important in this system is that these novel correlated states are very tunable. So of course, well, you can say, okay, we can tune the twist angle, and we can change that, and of course we can change temperature and the doping. Okay, so with this gate, which is what I say, having the possibility to dope with a gate it's very important. Now, but there are, because it's a 2D material, there are other possibilities that one can do, and because how is the origin of these flat bands. So for example, well, the origin of these flat bands, it's a bit complicated, but it's in any case, it's associated to how the two layers see each other. And so then one way to change these bands is applying pressure, because we are changing this interlayer coupling between them. So, and this was seen shortly after. You can see here, so if this is a case, for example, this is a twist angle with 1.27, and in which, if you look at the conductance, so this is a gray curve. So, well, here this is only the system without doping, in which is expected to be semi-metal. So, but then here you don't see much. In particular, you don't see superconductivity. You see some signatures here, some small thing for these half filling, like 2 electrons of holes. But what was found is that, well, applying pressure from above, they can really tune the superconductivity. See here. So you see here these minima, which are really associated. Well, these are really what you see here. These are the insulating states that were tuned. But here you can also see. You can also see how the superconductivity, so this how the resistivity vanishes. Okay. With when the pressure was applied. Okay. Another possibility that one can do is, so here this is effect. These are states that are associated to the correlation. So now, can we tune the correlation? So, well, in general, the interactions in a system are going to be controlled by, or are going to be affected, let's say, by screening. So people can play a bit with having, for example, the gate closer, but also there are some ingenious ideas. For example, here, what they did it was, is they have twist bilayer, and they put close to this twist bilayer another bilayer graphene, standard Bernal bilayer graphene. And then what they did, it was they charged this Bernal bilayer graphene, and in this way, they tune the gap of the insulator, something like charging that with electrons, okay? So they were able to tune that. Of course, well, one can also apply magnetic fields. So this is, to me, this is one of the most impressive figures that you can see in twist bilayer. So here you have magnetic field, and this is the filling from -4 to +4. All these, and this coming from compressibility measurements. So all these lines that you see there are correlated insulators. There are insulators, different type of insulators that have been created by the interaction, that are not expected to be there if you just consider how there are these paths. And so the fact that there are here some colors is because it's not only that there are, so they appear at different fields or magnetic field, the insulators, is that they have a different nature. So in particular, there are some of them, the green and the blue ones, are trivial in the topological sense, and the other ones are have some non-trivial topology. Okay, there are different. Some of them there is a charge modulation, and okay, but there are many different things. Okay, so just have in mind how rich is the phenomenology in this system, and how this is also something that will appear, how the correlation, the effects of correlations, and the effect of topology is mixed in this system. So one thing is also the system is quite sensitive to a strain. If you look at how the band reacts to a strain, it's amazing. Okay, and so this is, and of course here in this system you can apply strain in two different ways. You can apply strain, what it will be homo strain to both layers, or also heterostrain, which also happen a lot in just one of the layers. So this is an opportunity. At present, this is still a problem, because at present is, well, you put these samples in the substrate, and the strain is not so controlled, so well controlled yet.
Leni, thanks. Now we are showing here in this diagram the effect of the magnetic field on the electronic states of your material. But being graphene non-magnetic, could you explain why such a big magnetic effect on there? Why is it that obvious that magnetic field and maybe the Zeeman effect is going to have such a big effect, reduced magnetic field, 10 Tesla, not much?
Well, something, this dependence in many things is not so much associated to Zeeman, but it's orbital magnetism. So one thing is that the idea that we have from graphene, we have to put them away, because graphene, one thing that it makes that is not magnetic is associated. You don't form local moments because your bands are very wide. So here they are going to be very, very, very thin. So really in this system, people has in some cases observed real magnetic state, complete full polarization. But it's what I say here, the magnetism, it's mostly associated to orbital magnetism. It's associated, the way that you see it depends there, it depends in the topological states. It's really associated to currents.
Okay.
So I thought you were going to say, I was shouting. So at this point, at this moment, well, a lot of states have been observed in many different systems, but there is a lot of sample dependence. So it's still really not controlled both to strain and also to twist disorder and other effects. Okay, so so there is something that is not well controlled. Okay, so we have more possibilities to play with the system, because, well, all this started with this possibility of having this Lego, and then we can play with something, putting something on top of the twist by layer graphene. And so, for example, here in this experiment, what they did, it was they put wolframium diselenide. Wolframium diselenide has a strong spin orbit coupling. So what they observed is that they could find superconductivity at some angles at which, without this wolframium selenide, it was not observed. So somehow this is giving new ways. And of course, well, the usual way that in usual experiments, the twist by layer graphene is on top of boron nitride. In boron nitride, you have this honeycomb lattice, similar to the one in graphene, and in this, the lattice is very similar. So something that you can see is that, well, if they are aligned, the graphene in one of the layers and the boron nitride, so this is going to break the inversion symmetry, because the graphene atoms are going to fill, the two sublattices are going to feel different potential due to the boron and the nitrogen. So this has really be used to change topological states. They can also give rise to some commensurate, incommensurate effects and a lot of changes. But of course, the lattice is not the same here. It's not exactly the same. They're very, very similar. So I have told before that the main physics of twist bilayer graphene is associated to having these very flat bands and to this moire pattern. We can get a moire pattern having just two lattices, so the idea of getting a moire pattern is that you have two lattices that are very similar, but not exact, and are stacked. So you can have the same moire pattern, just putting the two lattices which have a slightly different lattice constant. So, and then, well, so this also gives us the possibility of having moire without twisting. Okay, and in particular, if we align, so if we even not align if we align the graphene on the twist bilayer, so we can also create this pattern. And so, well, people started considering a different type of systems, not only just twist bilayer graphene. So what people realize is that if you have a vernal, so standard bilayer, trilayer, pentalayer, tetralayer, with a specific stacking, but so far without twisting. So in this, the one that you see, this is what is called the rhombohedral stacking. So already even without moire, you have the tendency to have in some region of momentum space some flat bands. The bands are a bit flat. They are just in some very close to the K points, but you see that there are some region here that are quite flat. So if now we align this with the boron nitride, so one can isolate these bands. You can see here, for example, so this is these bands that are going to, because we are going to follow all the bands. Okay, so we can have moire flat bands without twisting. Now, here there is also another tuning knob, which is the perpendicular electric field. In some systems, the bands are going to be very sensitive also, and even we can open band gaps associated to put in a displacement field perpendicular. So you can see here, for example, how this band changes from here to here. So here you see we have this isolated band. Okay, so then, well, quite soon also people observe states in correlated states, insulating states in this is for a trilayer in this rhombohedral trilayer aligned with boron nitride. Okay, this is not twist bilayer graphene, this is another system. So, well, here people has also looked without the moire, without the boron nitride, and some of these states appear. So there is a bit of discussion here now how really important is the moire pattern, but for some states, it's for sure clear. And in particular, so one of these systems, in fact, the pentalayer has been seen recently. It has been the second system in all the known materials in which fractional quantum anomalous Hall effect has been seen. The first material was discovered only a few months before in another moire compound. So, and now there are other systems, the tetralayer and the hexalayer, that are also giving a lot of novel states. So we are not bored in this field. Okay, so far we have been with these multi-layers without twisting, with the twist bilayer, but of course there are other possibilities. So now that we play with the stacking, we can really have more complex system. For example, here you can see a standard bilayer, vernal bilayer of graphene, rotated, so one twist angle and another bilayer. So it's not just monolayer, twist angle, monolayer, but bilayer, twist angle, bilayer. There are also flat bands in this system. They are a bit different, but there are some flat bands. And here, well, if you see, this is experiment. This is people is changing the doping here. This is just with top and bottom gates. And this is a perpendicular electric field, where I say the system is, these bands become gap. So you can see here, these two states that you see here, this is adding 2 electrons or 2 holes for the system. The system was expected to be metallic, and it's insulated. So these are correlated insulators, which are due to the interaction. And of course, well, we can have, why just having two twists, so we can have tri-layer, pentalayer, twist, in the sense that we can have here, let's say here, this is theta and minus theta, the tri-layer. This is theta minus theta, theta. And you can see here, if you go to the 2 layers, 3 layers, 4 layers, 5 layers, we always find this is just this alternating twist angle, and we always have flat bands. The band structure is a bit different, but we are always having flat bands. The angle at which they appear it's a bit different. And in all these systems, in all these up to the pentalayer, you can see here how the resistivity is going down. So there is this superconductivity associated really to this twisting process. If we have now these angles, we can of course have them different, right? They don't have to alternate. So you can have them opposite that it was before. You can have them equal in both directions, and they can be different. So all these systems are giving us different states, is why I say as soon as we change something in the system, the phenomenology is really changing a lot. Okay, so far we have been with graphene, but there are many other two-dimensional materials. And in particular, we can do the same game with another one. Let's say, for example, with the chalcogenide that people have studied a lot in the 2D form. So in this system, so there are, so each monolayer in reality is like a 3-layer. So in the middle, there is this transition metal, and here there is a chalcogen in the top and bottom layer, and this is the lattice structure. Well, they can order more than one lattice structure, but the one that has been studied the most so far is the 2H. Now here, there are even different ways in which, if we say that they are rotated like 1 or 2 degrees, we can start from what is called an AA stacking, in which they are one of the layers. This is a twist by layer, one of the layers on top of the other, and then rotate a bit. And so we will have this alternation. And we can also do it in terms like the AV stacking, so something like this. So the symmetries and the states properties that are observed are different, because in this case, these two orderings, before I didn't say that, but these two orderings are going to be inequivalent, okay? Another difference with graphene is that, well, graphene is a semi-metal, but these systems are semiconductors, okay, the chalcogenides. So here, so the people have seen that flat bands appear, but they have a different nature, okay? They are in fact associated to doping this valence band with holes. And what is interesting, it's going to be important where in the brilliant zone it's this maximum. And in particular in this system, what is its key property is that spin orbit coupling is large. And in particular, when you have this maxima at the K and K, so at the edge, these K and K prime points, so you have what is called a spin valley locking, in which so there is a splitting of the bands. This is already in the monolayer, and so at K, the bands have a given spin, and at minus K at the other point, they have another spin. So there is this change. So these systems are also going to be sensitive to perpendicular electric fields. People have studied both twist dechalcogenides, in which the two twist materials are the same one. This is what is, or in which the two the two materials are different. Okay, so you can do both things, and again is that you can, as I said, you can do AA or AB stacking. So for a while, it was thought that superconductivity, or well, it's not that it was thought, it's that it was not found. People didn't find superconductivity in this twist structure in other systems except graphene bilayers, graphene moires. Very recently, it has been confirmed in this compound that superconductivity can also appear, okay? And you can see here also how this superconducting region, which is what you see here, this is, again, a perpendicular electric field, is in between two quite very insulating states, which are also correlated states. So we have a lot of this. Well, this is also a very important twist ballet graphene. This was the compound. This is twist molybdenite, the compound in which, for the first time, this fractional anomalous Hall effect was observed. And now, more recently, they have shown fractional spin Hall states. So, well, you see that people is finding states all the time.
Just ask one question.
Yes.
In this figure, is it fully superconducting or the resistance is saturating at in the second one? Yeah.
This one, I think it's people has really
Because I mean, if I see the color scale is starting from 10.
No, but I think that people consider that the real superconductivity is below here. So it's that somehow it's in these 2D materials does not drop so sharp that it's,
okay.
but this is quite new, so it's
Okay.
So far we have been with twist systems in which all the states which appear are really linked in the moire to this formation of flat bands. But we can also create moire systems in which each of the layers already have some property. Like, for example, one can twist with like it happened here in the chromium iodine, one can twist material layers which are magnetic. Okay, so this is what they did here. Well, there are different ways. This is the structure in which they can stack. And what is interesting, I was interested in this system is that you can, depending on how is the stacking of the, without twisting, depending on how is the stacking between these layers. So the ordering between the layers is expected to be ferromagnetic or is expected to be antiferromagnetic. Okay, so if you stack the layers in a way like this, you expect to be okay. So in a way that is this error stacking, you expect it to be ferromagnetic. In a way that is more like one on top of the other, you expect that to be antiferromagnetic. But then, because in this more heterostructure, the stacking is changing spatially, so you can also have domains. So you can engineer new spin textures in the plane, like twisting this state. So this physics that I'm showing this material is not physics really associated to the flat bands, but it's a different type of states. So, well, as we will hear a lot later in Nini's talk, one can, of course, can start. It is now starting twisting oxides. Well, these are the results that the other day Jacobo presented here. So there can have also non-trivial ferroelectric textures associated to how the atoms reorganize in this system, but also people has been twisting cuprates and observing. So twisting cuprates, what people has done is really coupling. Cuprates are D-wave superconductors, and so what they in this twisting, what they have played with is the way in which these two superconductors see each other, and they have found also twist angle dependence. So, well, my time is over. I just want to tell you the last thing is, so well, these are all a lot of absolutely great states. There are many more that I haven't talked about, so and many systems. So some other thing is, one thing is the part of studying the system fundamentally, which are really fascinating. Another thing is, well, can one invent something new, or engineer devices? So one thing, direction in which people is going is, because this system can be controlled with gates, like the correlated states can be controlled with gate voltages. You can make that the system is insulating or superconducting, just changing the doping with gate. So there are people is trying to do, for example, some junctions like with several gates and controlling the system in a way. But there has been also a very interesting discovery that, well, also Nini will talk. There is a new microscope. Already 4 years ago, there is, well, not 4 years ago, so 4 years after the discovery, so it was presented a new idea of having a microscope with the idea of twisting. So here there is a tip with a 2D material, and here there is a rotating frame with another 2D material. And so one can really change the angle in situ and look at the properties, but also one can look at the band dispersion. One can measure the band along certain directions. You can see here, to have an idea, this is from the first paper with this quantum twist microscope, these are the bands for which are predicted in several direction in K space for a 2.7 twist bilayer graphene. These are in blue. This is the theory in these points the experiment. So you can see it's really fascinating. But you can also see there is a second paper about the phonon dispersion of twist bilayer graphene. Well, in fact, this is one graphene rotated with another one. It's that figure looks like a theory figure. It's how impressive and how sharp it is. So it's really amazing. And well, so there are already several labs in the world that really are installing. Some of them, I think, they are already starting to measure with these new microscopes. And okay, so well, I hope that you have got an idea of how extremely fascinating is this new field of twistronics. Really is reality is very, very far beyond imagination in this system. Every 4 or 5 months, the field is completely shocked with a really very big discovery. So it's really, we have many different non-hetero structures, many different materials to play with. One can do more systems without twisting. So there are many different types of correlated states. In general, what we see here is the interplay in many of these systems between strong correlations and topology. So also from the fundamental point of view, it's not just a system in which you find some states, is that you find states that you have not found before, and sometimes they are really still not understood. Well, there is really one of the key aspects is that there is really impressive in situ tunability. Okay, thank you.
Yeah, thank you for a nice overview about the physics of twisted material. So now time for questions.
Thank you, Leni, for introducing the field. So my question regards which is the understanding of the superconductivity in these systems, in particular in the sense that these are very dilute superconductors, right?
Well, this is very dilute, but if you think, so here and later I will, in the second part, I will discuss a bit, is if you think in the large Moire unit cell.
Okay.
So you just, the electrons, you don't see this, so it's really dilute if you go to the density, but from the point of view of the
you have then the picture is that you need to think about the Moire unit cell.
Yeah, in that sense, so I think people is not discussing much, but in terms of, for example, twist bilayer graphene, is this phonomediated, is this electronic? Well, so, well, it's still not known. Most of the people believe that it's due to electronic correlations. It's unconventional. In some of the other systems, for example, in the twist trilayer graphene, and also because, for example, there is also superconductivity in the graphene, in the tri-layer and the bi-layer of boron nitride. Well, okay, something that I didn't say is that after, okay, so I will say later. Well, in these systems, for some of the states, because there are different superconducting states, so it goes, so the system remains superconducting beyond the Pauli limit in the sense that is telling you that it's unconventional, maybe triplet superconductivity. But it's really not, for that ones it's known, but for other ones is not clear. In terms of order parameters, I think people has proposed all kind of order parameters. That so there was one experiment saying that it was nodal, but it's not necessarily confirmed. So that's really not known and really open. And what I wanted to say is is like in this bilayer or tri-layer on boron nitride that I mentioned, that you can do moires and you can discover new state. And after that, people they say, okay, we don't align it with the moire. People saw many states, some like polarized, spin polarized or valley polarized states, but people also saw some superconducting states. So let's say bilayer graphene without moire is superconducting at low enough temperatures. And tri-layer graphene is also, rhombohedral tri-layer graphene is also super. So somehow is that people is also going back to devices that they have in their shelves before and just lowering the temperature and also finding new things.
Okay, so very interesting. Thank you. Thank you very much.
Okay. Thank you for the very interesting talk. I have a question about the TMD that you showed before. Maybe it's too specific, I don't know, because I know that TMDs are used for spintronic devices, like to perform some spin charge conversion. No? But recently they are seeing that in the bulk form, they are not very suitable. Also, if in the last 10 years, they claimed a lot of interesting stuff. Do you think, or do you know if the twisted TMDs can have like different properties in terms of spin channels available at the Fermi level with respect to the bulk? Because now what happened is that in the 3D, like for instance in the molybdenum telluride, they observed that a lot of observation that they did were extrinsic, like not like in the case of spin charge conversion, not really, because if it's a white semi-metal or something like that.
Well, so here, so what it has been observed for the dichalcogenide in bulk can be quite different. Here already even the dichalcogenide from the bulk to the monolayer. Yeah. But here is that you change all the band structure. You really create flat bands which are associated to how the two layers see each other. So in the dichalcogenides, so people is observing a new world completely, as so impressive as the one of graphene or even more. So it's the dichalco. I have mentioned a couple of cases, but well, the field is really exploiting. But what I say, I think people, it's intrinsic associated to these flat bands that you.
But do you have an idea if there is a degeneracy in the, like a spin splitting?
Okay, so for example, this.
If you know a board, a paper.
You say this is spin splitting that I put here in the sense that in each valley that you have these bands. This is each of the valleys of the K and K prime. This is the spin splitting. Okay. And so, for example, and this is one thing that I was going to mention later, is, so this is, I think nobody is questioning that. I don't know if this is the splitting that you referred to. It's that is that in each of the valley you have one spin, in the other valley you have another spin.
Yeah, to have at the Fermi level two spin channels degenerate. Like not sorry.
These are
not
not degenerate, these are splitted.
Okay.
And so somehow, and this is specific on the chalcogenized disease, but the point is that they are splitting already in K space, in the sense that you have in one K, you in the monolayer, in each of the monolayer, in one of the valleys you have one spin, and the other valley you have a spin down. So that's going to be later important when you put the two layers, how you put one layer on top of the other, because maybe you are trying to
you compensate or not.
No, more than compensate, that you cannot have tunneling.
Yeah, of course.
So if you have a spin with the other spin, you can have tunneling, spin with up with a spin down. Well, later at the end is that the system relax, and so spin is not so well conserved. But so somehow the coupling between the layers is very different due to this specific thing. But so I think that with the splitting, that's well. So somehow it's happening.
Because also
because otherwise the degeneracy of the bonds, it would be much larger, and it's the one that is suspected.
Because also you show the fractional Wall effect, and so maybe they could be interesting to try these materials like the twisted molybdenum telluride in a real device to do spin charge conversion with respect to the bulk. I mean,
okay,
so it seems that it has a completely different topological properties.
But it's that the topology of this band is very much associated to the twisting. I don't know exactly if that can be done. So I know that, for example, in that, to understand these fractional states, there is a lot of issue on how is the relaxation of that lattice. But I don't know, maybe I'm not. So I haven't worked specifically on the molecular on the chalcogenide. Maybe there is something. I say this is just we are opening Pandora box. And from each Pandora box, there is another Pandora box and another Pandora box. So it's a lot of things are.
Oh, but it would be interesting to try.
Okay, yeah.
Hi, Lana. Okay, so the key point is to get these flat bands, no?
In most of the, well, in the graphene and in the chalcogenides, for example, in the chromium iodine, it's more.
But more or less all conserve this kind of the same symmetry. So this hexagonal, can you rationalize it and say, okay, if we change the symmetry, we could get
you say like
something
a square
else.
lattice or something? There is, for example, I have seen a paper, I think it was barium titanate, right? No, or strontium, I don't know, well, one of these. But we were talking this morning, barium titanate, probably barium titanate, in which they also get flat bands theoretically. So I think it's in these systems so far, people has worked with this hexagonal lattice. And they are in fact also having this minima, maxima, or well, the valleys are or at gamma at K point or at K point. Recently, people has proposed, still have not done experimentally, also other type of systems. I think like it's hafnium sulfide or something like, in which there is a different type of, so you also have this hexagonal lattice, but the valleys are at other points in the brilliant zone, so that changes the degeneracy. And I think now people is starting to look more at other tetragonal orthorhombic systems. So in the future, there will be more. What happens is that in the van der Waals, which is what has been mostly studied so far, these lattices appear, but the future is open.
More just a curiosity, when you show the at the very end the twist angle for the oxides, for the cuprates, the angle is strange, 46. This is because it's 1 degree to 45.
Well, that was associated to so here it's you say so here. Well, first is the angle is all the angle. Okay. Okay. This one. Well, that was the figure that it gave. They gave there probably because they have this very nice or whatever. But one thing is that in general they study all this region because then later. So normally when you have the two cuprates, because it's a D-wave superconductor. So if they are at 45 degrees, so the Josephson coupling will not be expected. And somehow, well, they see that, well, it's very strongly suppressed. but not completely suppressed at 45. In fact, they see that in reality, what they are observing is it's tunneling of several Cooper pairs, so like what they call higher harmonics, but also is, and then well, they later play in all these regions. So somehow it's this 46 is you see here, all these points are, they have many angles.
More questions?
I would like to follow up somehow the question by Jaume, trying to rationalize when you may have these effects and so on. And basically, as you mentioned, and Jaume recognized as well, that the flat band is the key parameter, right?
For the appearance of the correlated state, the flat band is the key parameter, but for example, not for this physics or this physics. Here you don't have flat band, but for the other ones, the absolutely key is the flat band. Yeah.
Now, if you start with a single layer, you don't have a flat band. You have a flat band when you put one layer on top of the other. And now that brings me the question. No, first is that at the beginning, when you have a band which has a given curvature, that is this is due to because the orbital combination from the combination of orbitals in one side and in the other side in the lattice is k-dependent, and that gives you the dispersion, right? And this you the parabolic band or whatever is depending on the dispersional phase, kx or whatever. No? Now, when you put one layer on top of that, on top of this one, you put another layer. It turns out that the orbital mixing is no longer depending on k; it's flat. So this is why you have a flat band. Okay, why so? Why the mixing of orbitals is not depending on a phase?
One thing is
no, but in the first slide it was.
Yeah, but that I'm going to show one. I think it's probably no. Okay, no. So it's not this. Can I go? Probably I have this. Okay. Is that I have one that I took out because it was going to be too long, and probably this one. This one. You were thinking on this, right?
Yeah, maybe.
Okay.
Yeah.
So the question is here. Okay, so the origin of the flat bands, in fact, is different in the chalcogenide and in the graphene. So here, what happens? So one thing is because this Moire unit cell is so large. So when you have to think in the momentum in the Moire unit cell, you're going to be very, very close to the Dirac point. Okay. So this is plotted like this, but really this mini Brillouin, let's say, is going to be 10,000 times smaller than the graphene units Brillouin. Okay, so you are very, very close to the Dirac point. Okay, now in the case of graphene, well, is that these are the top and bottom Dirac points. Then you start hybridizing them, which in fact, and later I will also mention is the ways in which the two layers hybridize is not that they hybridize in the same way in all the Brillouin zone, is that normally, in fact, the main hybridization is associated to channeling or in the center of the unit cell or at the vertices, because it's where you have atom over atom. And then, well, here there is a complex destructive interference process. That is for twist bilayer graphene, what gives the flat bands. So, and because of that, this is what really gives rise to the topology. It's not just something simple in which you say there is a very complex interference process. In the chalcogenides, in fact, it's easier, and so you have bands which are quite flat in close to the top, and so somehow when you are doing the moire, with a bit of hybridization, they become flatter. So there are different ways in which people is getting these flat bands, but in graphene, it's a bit. So what you can see is that here, when you start hybridizing the two, these are the two Dirac points of the two. So one Dirac point of each of the layers. Yeah. When you start hybridizing them, you see that you start these start going down. They become flatter and flatter. and they can be completely flat. So of course the dispersion, maybe the dispersion that you are thinking that it was so large is that it becomes other bands that are high.
That would be
in energy.
equivalent to avoid, I mean, if it's flat, that is like an atomic limit. It's like not having any orbital mixing.
No, but this is what I tell you. There is a very complex, this is not an atomic limit. And it's a very complex interference process. What happens here is
it's any phase contribution. Yeah.
It's not so, and in fact, this is why I say the flat ones in Swiss layer is that you really cannot see them as just even if they become completely flat, they are not. You cannot think on them as atomic insulator. And in fact, later in the second talk, I will mention something. They are mixed to the other bands. It's what I say. This is a complex process, and this gives rise to a lot of the properties. The fact that it's not just an atomic insulator.
Hi, thanks, Leni, for this inspiring talk. I have a practical question. When you mentioned about the fabrication of these heterostructures, 2, 3, even 4 layers, how do they control the stacking of each layer? Because for me, stacking 2 is already a nightmare.
Okay, so one thing is that these are van der Waals materials. So this is
okay.
The only ones which are not van der Waals that I have mentioned is the twist oxides. So these are van der Waals, that's easier. And so normally what they do is, well, they have the tear and stack. So they exfoliate one layer and they put in another layer. And there are even some people in which, well, for example, for boron nitride on graphene, or they even manage to rotate them in situ. So, well, with some, not only with the quantum twist microscope, but also there is some way in which they perform some device in which they even manage to have them, well, warm it up, rotate and pull down. But it's key that is van der Waals. So that is what has made that easier. Yeah.
Okay. More questions? If not, then thanks again, the speaker. So now we will have a real 5 minutes here. Okay, so after 5 minutes, we will meet for the next session.
Okay, I think we can start this second part of this session. And I am Emanuele Longo, I'm a postdoc here at ICMAB, and I'm going to chair this second session of this school. And please, I ask to Professor Nini Pryds to come to the stage, and he's going to present a lecture entitled Twisted Oxide Membranes, Fabrication, Transfer, and Stacking, Current of Advances and Future Outlooks. So please, the stage is yours.
Thank you very much. Can you hear me now? Good. But it's a good start in the morning. Yeah, I will, first of all, again, I'm happy to see so many people here, and I can see there is also some people there, so people are still awake and the end of the week. So I'll try to keep you somehow awake with going a little bit to the methodology. I think Leni was doing really good, and you will learn maybe more about the physics of twisted material. I will look a little bit more about the methodology and the methodology, which I mean is the fabrication, the transfer, the stacking of freestanding twisted oxide membrane. I will try to put it in perspective. Where do we stand now? What are the challenges? Where do we want to go? So I hope that, and if you have any questions, just interrupt me. So what we see here is a twisted membranes of strong cerium gadolinium oxide. It is in fact ionic conductor. It's one of the conductors that we use for solid oxide fuel cells. And this is just to show that you can, in principle, you can twist any material. The question is how good are they twisted and how accurate can you make it, and many other questions that I will raise through my talk. Again, I would like to I would like to start by acknowledging the people now who contributed to the work that I'm going to show you today. Yesterday, there was some other people, and these are the international collaborators that contribute to the work that I'm showing you today. So I thought to start with graphene because I wanted to put it in perspective, but Leni was giving an excellent, I'm not going to compete with graphene, so I just wanted to put things in perspective and to say what can we learn from graphene and where can we move ahead. So I'm not going to talk too much about it. Everyone knows about graphene now, so I'm okay with this, and I'm trusting that you know about it. What I want you to remember here is that you can stack it different ways. You can do a single one. You can put the AA when you put one on the top of each other. You can just move it. Exactly what Leni was talking. I think the message that I want you to remember from here, that the detail of the stacking matter a lot. And it will come later available or reasonable when I will talk about the oxide. So it's not just stacking. Stacking is important. For example, as far as I am aware of, the AA is not so energetically favorable. On the other hand, in graphite, you will see the AB configuration. So there is different configuration, and we need to think about what is the best. So one thing is the stacking order, but one should think also about the twisting. And again, I'm not going to say a lot about it, but as Leni was showing, so if you're starting with one layer of graphene, you put another graphene layer, and then you rotate it. Basically, the real space rotated at a certain angle, the momentum space rotated. So you have the Dirac shift with the shift proportional to the angle of rotation. So it's important. So rotation can change something in the material and separate the momentum space. And I think that Leni was also hinting in this direction. And what I want to say here that it's not just the interaction, it's not just the putting layer on top of a layer, which will make the job. The layers should interact with each other. And the interaction of the layer, it's also true for the oxide, in my opinion. In the case of graphene, you have the interaction and you have the band opening, and which defining by the W. So this is the tunneling between the two layers. At the end of the day, you got the flat bands that was discussed earlier, and I'm sure it will be discussed after my talk again. The flat band in the momentum space, in fact, in the real space, it looks like a concentration of, it is the concentration of electrons at the AA, and which are weakly coupled to the AB configuration in the real space of the material. The reason why I'm saying it again, no, I'm not going to talk about the physics of graphene. What I want you to remember from here is that you get an unusual correlation behavior in this system due to the rotation of the material, such as mode insulator, superconductivity, and many other. This is happen at a magic angle. And from here, the reason why I show this one is because there is another system which is strongly correlated, and this is a system which is intrinsically strongly correlated. And these are the transition metal oxide. The other ones happen because of the rotation. Here we have a correlated system which is due to the electronic structure of the material. So we have the 3, 4, and the 5 d electrons. These are coupled with the oxygen and form the transition metal oxide. Transition metal oxide are strongly correlated system. In a simple explanation, what does it mean? It means that the electron not anymore live in a sea of electrons and not interacting with each other. They do see each other, they do feel each other. And due to this interaction, what happened is that they are coupled together through the electron spin, orbital, and lattice parameter. And this brings about new properties in the material. And this is what makes this material so interesting. So you can get ferroelectricity, you can get electrostrictive, piezomagnetism, and even multiferroicity in the material. So these materials are very rich intrinsically in properties, in my understanding at least, compared to the material compared to the 2D material, which you need to do something to the material in order to get these correlations. Today and yesterday, we have seen that we can take this material and make them as a freestanding material, so we can release them and move them from one place to the other. This was yesterday, and now we can do, basically, we can take now transition metal oxide and transfer them to whatever we wish to transfer them, if we know how to transfer. So what is interesting in the field? So what I want to say here is that currently, we've been working many years with, or people have been working many years with epitaxial complex oxides, grow the material, they are bound they are stacked and bound to the crystal, to the substrate, and they are also determined, their property determined by the substrate. Now we can release them, and we heard about it yesterday, so we can release the layer out of it and use it to whatever we want to use it. On the other hand, there is another field of research of the low dimensional van der Waals material system with many people working many years, and they have optimized the way that you can stack, twist, and move material. So my point about it here is I think it's the right time that we can combine these two areas together and try to do the stacking and twisting of the material. So we should learn from the two fields what people did in the 2D material, how do they twist, how do they stack, and then try to implement some of the knowledge to the field that we are working on. So that was somehow some of the motivation for the work. So this brings about a new opportunity for a new material system. Why? Because we have material which are correlated, and therefore there is a lot of properties. Some of them are semiconductors, metal, insulator or magnet. We can also order them differently, so we can put them in different order, and here where the order play a role. And on top of this, you can, it's not working anyway. There's a video there, and you can twist them also. So there is 3 degrees of freedom where you can play with the material, and you can see that it's infinite amount of possibility that you have. You can take different material, you can order them differently, you can twist them differently, and play again. So we have a lot of, I mean, the playground is really rich of possibilities. I guess here I didn't thought to talk about it, but here the modeling and the simulation play a major role. I mean, because where should we start? Where should we finish? What should we do? And we should think about it. And maybe at the end of my talk, I will give some hint which direction we should go. Good. So how do we make the film? And yesterday I wanted to speak about that, but I thought I would keep it to today. Usually the way that we are making our films, most of the people I know of, at least, doing with the PLD. So we're starting with a single crystal material. Usually when we buy it, it's double terminated. Then we chemically and thermally etch it. We're ending up by some terraces. The height of the terraces, this is strontium titanate, just an example. The height of the terraces is about 0.4 nanometer. You take it and then you use it in whatever system you use. We're using a PLD, and then you bond it. And this is just a snapshot showing the plasma propagation from the target to the substrate. This is one way of making the film, and therefore the membranes that we want to make. There is this is also, so this is just snapshot from the lab that we're working. We have a PLD coupled together with a sputtering. We have some system with the lasers coming at each place, so we can work at the same time a different position without interrupting each other. But that was only PLD. Yes, there is other ways of making the material, such as magneton sputtering. And I know there is some activity here about magneton sputtering. There is hybrid molecular beam epitaxy. There is some people working on freestanding beam hybrid molecular beam epitaxy, the group of Jalan Bharat from Minnesota, and sorry again, and here in the place with Mariana, you're doing, among others, I know that you're doing also other things, but it was the first time that you came here with ALD. I think ALD is the challenge here is you want to make it as large as possible with a process which is as close as possible to the, I would not say to the market because we are far away from the market, with the possibility of extending this. So PLD is a good opportunity, and I think that also magnetron sputtering is another good opportunity to extend it after we understand how to make 5 by 5 millimeter. But it's good to start somewhere, and it's good to think 2 steps ahead. So the way that we are doing the membrane, we talked about it yesterday. I'm not going to repeat my talk. I just want to say that during the talk today, I will talk only about a water sacrificial layer, the way that we're doing it. So I'm not going to talk about other ways. I also, during my talk, there is different ways of exfoliating and moving material. I will concentrate mainly on the scooping and modified scooping, I would say, because we're doing it a little bit different in some way. So these are the 2 things. It will be sacrificial layer with releasing the material with water at that case. And then I will use the scooping in this talk to illustrate some of the things that we are moving, where we move the membrane from one place to the other. These are some people ask me, which material do you do? In principle, we can do many. I mean, this material we have produced in the lab. But, and I think that the point is not about making the material here, is how do you make the material? And I think what we're putting a lot of effort is on strontium titanate by itself, because we want to understand how to find the right methodology of making the material, transferring them and moving them to another place. So when we're doing all of this study, we're doing it on strontium titanate, but we have some project on the different membranes that you see here. And there is many other membranes that other groups also work in the world. I think this slide is important because, in my opinion, I wanted to list what are the problems, what are the challenges that we have currently in the field when we want to twist the material. So one of the things that is challenging us is the strong ionic bonding between the layer. So once we put the material on top of the other, we heat it, we treat it, whatever we do, it bonds somehow to each other, and then we cannot move it anymore. So it's not like the Van der Waals material that it's a weakly bond, so you can twist it, you fix it at a certain time, and then it's fixed. Usually it's not, if you put 2 materials on top of each other and put them together, they are not just exactly the same way, they just snip a little bit to find the right condition in order to fit themselves. This is what caused some other effect that I will talk a little bit later in my talk. So overcoming, how do you overcome this? How do you find a way to get a good bonding, but also later to twist it, if you want to continually twist it or to twist it in general? So this is a challenge. The other one, which is incredibly important, is the interface cleanliness. So we take 2 surfaces, which are very thin. I think, Pep, you say yesterday, correct, you put them in the water, you take them out, you move them here, they are dirty. They are not clean as we want to do. When you put them together on top of each other, how sure are we that we get the right conditions? And on top of this, how sure are we that we get the right condition in different labs? I mean, because I can do it in my lab and I may be taking care, other people doing in other place, less care, and I don't know what will be the results at the end of the day. How can we compare results? So this is important to pay attention to the cleanliness of the interface. The same way is important to take account to the surface termination. So how do we terminate the surface? What is the what are the conditions? It's also related to the cleanliness. What are the conditions of the surface termination that we need to take care of? And the fourth one is also absolutely important if we want to work with twisting, controlling the twist angle. How can we control the twist angle? I mean, if I'm fishing a membrane and I'm fishing another membrane and I want to put them together in an angle of 1.5 or 1.05, how do I do that? Maybe I can do it once, and how do you do that? How do you do that? It's impossible. So we need to find a way, we need to find a methodology, in my opinion, where we can find a way that we can all do something that we can begin to compare. Because I feel the field is still young and we're still doing things, and it's very difficult to compare things, and very difficult for me, at least, to go and repeat some other people's work at this point of the field. So this is important that when I'm saying all of this, because I'm trying to motivate people in the field to think about it and try to find solutions. So it's not just to making film and to go to look at the physical properties because it's interesting. But what's the next step? What if I want to repeat it? What if I want to do it more? It's impossible, at least at this point, I think. This is my view. And then interface disorder. So there is disorders at the interface also because of the matching or mismatching of the layer. We need to think also about it. So these are the current challenges with the twisting. And I will try to go through some of them. What do we do? What other people do? And I don't have solution to everything, but I have some ideas about that I can share with you. So let's look first about interface cleanliness and surface termination. I think it was yesterday or the day before yesterday. I think it was Jacobo who mentioned about the cleanliness of the surface, where we see some gaps in the surface and we are not sure what is it. So let's look a little bit in deeper. What is it? This is a work that we did in my place. So here we took two strontium titanate. We put them together at the angle of approximately 10 degrees. And then we bond them together. How do we do that? So what we did is we took the surfaces, we cleaned them as good as we can. So meaning that we clean it with acetone and then with plasma etching. We put them together on top of each other. We heat them to about 550 degrees in a reduced atmosphere in order to clean the surfaces. And this is what we get. So we got two layers, which are rotated according to each other with 10 degrees. Oops. So, and when we saw this first time, you could say, okay, you have a bond in one place, you have a gap on the other place, so it's not really bound to each other. We think that it's bound to each other at this point, both from the reconstruction here that we've seen, also from doing an analysis across the different layers. But the contrast, the question is why the contrast is, where the contrast, because otherwise you will see something which is completely homogeneous all over. I think the contrast, we are doing some work on it. I think the contrast comes here from dislocation. So we think that there is a dislocation net when you twist the material. So it's not just the moire which is there is also dislocation because the material tries to fit each other and cause the dislocation at the interface. So we did yields and we could see also that there is some oxygen vacancy in there. We can see also the moire structure. So we observe things that people observe regularly in the 2D material when you put two materials together. Now the question is what happened at the interface? This is a work which already published in 2019. It is two single crystal strontium titanate, and they put them together. They put a pressure of about 1.2, I think, gigapascal. They heat it up to about 1,200 degrees, and then rotate it to each other. And what they see something that we have observed. So you see some reconstruction in some places, and some places it is not reconstructed. There, in this paper, and I cannot show all the figure there, they've concluded that it's also a dislocation net at the interface. I don't know. Currently, what we're doing currently is we're trying to look for dislocation net directly and see whether we can see the dislocation at the point. At this point, we just assume that it's dislocation, and from that on, there was other groups who started also to look at this. This is the group of Jochen Menard in Max Planck Institute, and they looked at how can you bond the two material and get a good bonding. So the first method, which they call a state-of-the-art method, you can see. So these are real images. When I saw it first time, I thought it was a cartoon, but it's real images. So what you see here, you see a gap in between. So the blue line is the gap, and the state-of-the-art method, it's, as far as I understood from the paper, it's just they put the membrane on top of this, they heat it, and they see the reconstruction at the interface. Then they have they develop a new three-step method, and the three-step method goes in that way. The first step is annealing the substrate with laser annealing. Then the second step is putting the membrane under elevated substrate temperature. So they heated the substrate, they put the layer at elevated temperature. And the third step, they anneal everything with the laser, heating in oxygen. So they end up by having a perfect matching. So remember, this is strontium titanate on sapphire. So sapphire is the substrate, strontium titanate is the layer on top of it. What they also observe, and I don't have a lot of time to go into too much details here, they also observed that they saw about 2 angstrom space, or a gap between the two layers, and a detailed analysis showed that the bottom layer, basically the atoms that sits on the surface of the bottom layer, is the aluminum, and they see the strontium on the top, but they are a little bit shifted, and from their analysis, they see that there is a sort of slight distortion of the strontium towards the aluminum. And in the paper, they say that it can cause, for example, chirality or strain distribution at the interface. I think my main message here is that we need to think about the interface, how to make the interface good and intact. And it seems like it's working quite good in these conditions. There's another work recently at a group of Andrea Caviglia in Geneva, and what they did is they took strontium titanate membrane, they put it on a strontium titanate doped niobium membrane. As far as I know, and maybe, I hope I'm not mistaken, they didn't treat it even, they just put it on top of each other, and they did the following. They took the first sample and they used it as a reference sample without heat treating. The second sample, they heat treated at 550 degrees, and the third sample, they heat treated at 700 degrees. After heating the sample, they put them in the microscope, and they use an E-beam writer to scan the area there. And it's turned out to be that for the first layer, without any annealing, they could see no reconstruction. 550, they could begin to see reconstruction after 250 to 500 frame. And in the case of 750, they could see the reconstruction already after 50 frame. I think the take-home message from these results and the other, that we need to activate the surface somehow. We need to give it some energy in order to reform or to reconstruct and form the bonds. On top of this, the cleaning of this. So they have investigated, they saw that there is some of the impurities they've seen before are removed due to the heat treatment of the material. So the idea is that you need to have a surface cleaning. And this is something that we are doing also in our place. So we want to, we're using our new national research infrastructure in the group. And so we have laser deposition here. We have also the other techniques here, but we're putting stacking, twisting instrument here, and we want to keep everything under control atmosphere. So control atmosphere is quite important. You want to work as less as possible exposed to the air of the material. So this is one. I don't think this is the only way. There's many ways of doing it. This is one way to avoid taking samples from one place to the other out of the air. The other thing is the heat treatment, and I guess the heat treatment at this point. I cannot think about some other ways at the moment. So this way of doing things, I think someone need to think about it. We are thinking about how to improve the condition of the interface. This is just a picture inside the material. So if we are able now to make a good interface, and the interface is good, how do we control the twist angle? So as I mentioned before, if we want to go to an angle of 0.5 degree, 1 degree, and we want to do it repeatably at different place, how do we do that? How are people doing it today, and what are the vision for the future? So this is a illustration of a paper where the authors took strontium titanate, they tranched it in a different position, and then they took a membrane, they put it on top of this, and then they used the tranches lines in order to align the angle of rotation. I think it's good once you're putting it, because then you know the angle. But if you want to determine the angle, predetermined, it's not a solution. It's just to illustrate to you how to put it and how to get an angle, not a particular angle. There is another paper here where the authors use the crystal structure as a reference. So they use it as a reference, and they put it in 0 angle and 45 angle, and they found some really interesting results that the magnetism is different whether you have 0 or 45. I would not be able to repeat these experiments, not because I don't trust or I don't think it's right. I'm just saying that I don't know how to make a 0 rotation, because there's no 0 is the most difficult, in my opinion. How to align something to something with no rotation of some degree, and some degree, as we see before. So before, small degree can give some more structure, can give some. So it's very difficult. We have to think about it. We have to think about how to control this in a real way, so everyone in each lab could go and repeat and do the same things. You cannot see it probably from the back, and that was the idea. I don't think you should see what it's not important. This is the way we're doing scooping. And scooping, we don't think it's the right way to do scooping. So what we're doing is the following. We're coming to the point where we have the polymer, we have the material, we have the SAO, we have all the stack together. Then we're putting it on a motor control vertical movement line. So we have a motor control, how do you call it, cantilever, you can say. And then we put all the stack together. And then we put it, for example, this is just schematic, but I'll show you some other picture later. So we put it in the water, we dissolve the SAO. Then we are putting it on another substrate. We're heating it to a certain degree, so we release the polymer. We clean it with acetone, we clean it with plasma etching. And then we go to another material, we repeat the same things once more, cleaning it together, and then we're putting one on top of each other with an angle. So this is a schematic illustration of how do we put something on something with a certain angle. But I was advocating all the time that the angle is important. How do we do that in real life? So the way that we are doing it, we're using a stacking and twisting equipment here. So what we see here is we have two manipulators here. We have a heating stage here. We have a rotating stage. Everything is controlled by computer. And it can be rotated with an angle of 0.001 degree. And what we're doing, so this is just for illustration, we're putting the cantilever here. We are moving it while we are observing it with a microscope, so we can see exactly from above what is the relation and what is the angle that we want to put one compared to each other. And the way that we're doing it, we have a motor control here, which allow us to go at X, Y, Z, but not just this, it allows us also to have a plus minus a degree of drop down, because this is something that we learn from the people from the 2D material. One of the things that they have in 2D material is that they get some air bubbles when they put the layer on the layer. So the way that they're doing it in this way. So it's just they're pushing in their understanding, they're pushing the air and then they're putting the material on top of each other. This what give this motion that we want to go. So we're using the different motion in order to try to put the layer on top of the layer and then observe the rotation of the material on top of each other. And then we have, like I said, we have a temperature control. So we need to heat it up and release, because we need to release it from the holder. So we can heat it, release it, and then everything is controlled by computer and by microscope. So the computer giving us a frame with the position of everything, so we can know where is the zero, and we can know what's the other degree of freedom, and we can go back to it all the time and know exactly which position are we working on. This is a way, probably there is different other ways. This is a way that we believe we can go further and repeat the material, repeat the angle time after time. We did some experiments, and these are just twisted angle, different angles, and we did some AFM, and we can see that the material is lying on top of each other, and after heat treatment, also the thickness is the same. So this is straightforward. It's the same pictures with the AFM. And what I wanted to say, and I cannot say more because we are in the patent, but I can tell you, and you have to trust me or not, it's up to you, is that currently today we are able to control a twist angle with accuracy of 1 degree. And we can also ensure that the interface is clean enough. We have a way of doing it. I hope that maybe next time I can show. My point about it, maybe you can find other ways. You have to think about how to put something on something with a certain angle and make sure that the interface is clean. Because maybe we can put it, but if the interface is not clean, then we did half of the job. So you need to do this, and the pattern. In fact, so I cannot at the moment say, but you just have to trust me. So we are able to do it today, and hopefully we're still modifying the things, and hopefully we'll be able to say to the community, because I think this is important, that everyone will use something that we can compare with each other at the end of the day. Yes.
But what is your zero?
The
reference zero. What is your zero?
Is the bottom layer.
So you go along the direction of the line.
Of yeah, yeah. So we have a layer that it's below, which we mark it on the computer as a frame, and then we take the other one and we put it compared to this frame with an angle. So, but we need to know the orientation, of course. So the crystallographic orientation of the crystal is determined by the edge of the crystal that we put.
Basically, when you exfoliate, you keep the edge
yes,
of the
yes
along the substrate.
Yes, and this is important. And this is important. It's important to have an edges which are clean and sharp, and it's important to follow up this one. Yes.
You never cut your substrate before release. Usually it's
we
always
do
5
something.
by 5.
Yeah. Yes. Okay, good. Let me continue. So again, the point is not to say. The point is that to say that it's important. It's important to make something, to work on some methodology which allow us to control the angle. That's the message. What about more engineering? So if we can make a clean surface, and if we can twisted at the right position, then the Moiré structure or the Moiré engineering came about. This is a perspective paper that we wrote last year. And we think, and it's not something, I think everyone who will think about it twice will come to the same conclusion. We just thought about it and wrote it. That what happened in the interface is not just Moiré. It's a Moiré, it's a chirality. We've seen it yesterday also with the work of Jacobo. And there is also dislocation. We think it's a combination, and we think that there is a parameters which couple them together. There is I don't say it's not universal parameter, but there is a parameter that couple the three structure or the three, the three units together. What I want to say, or the reason why we also thought about dislocations for the following reason. I mean, this is an example from long time ago. Some people work on silicon. So what they did is they took silicon, two silicon wafers, and they put them together, the thin wafers, and they twist them together. And what they see, so this is the twist. This is the twisting. This is the Moiré. This is the dislocation net. And this is from another paper. So you get a dislocation net at the interface. And it's not surprising. If you make this exercise and you take two lattices and you try to put them together, rotate them, you will see that you need to form some dislocation net in order to compensate for the movement. Since these are not van der Waals material, they will have to compensate for the large strain. So the strain cannot be forever large. They will compensate for the strain by forming dislocation net. This is and we are currently working on it because we want to prove or to show that indeed there is a dislocation net at the interface, and there is indeed relation between the Moiré and the dislocation net, some relation between them. This is something that we are currently doing. Yes.
It's a dislocation or it's a periodic reconstruction of the interface? Because a dislocation...
these are dislocations, and I believe that we have also dislocation. I haven't seen them. No one has seen them, at least my understanding. But these are dislocations. These are
also the pictures, the microscopy pictures that you showed us.
Yeah. They saw this dislocation.
I've seen none.
No, because you looked at it in this direction. They have also looked at the other direction. So it's a screw dislocations coming. Yeah, I think it was a screw dislocation coming from below. So no, it's not a screw. It's a, what was it?
There's the other edge dislocations. But I mean, usually around the dislocation,
yeah,
the deformation is huge.
Yeah.
And in the image, you should be able to see it. So that's why
this image or what?
No, not this.
The other one.
This is a completely different technique to get these images.
Yeah,
Diffraction contrast. But the other one is different.
It's exactly what you said, because that's why we're doing with another technique now, with another microscopies to see the dislocation. We could not see on this. That's why we're using another technique with the TM in order to see.
Conventional TM, you
exactly. So this is exactly what we are currently doing with another expert in the area who did work on this location. In fact, people who did something similar to that one, because we could not see it in other way. But we believe that there is a dislocation there. We need just to prove it. Good. So there was a lot of work over the years. A lot. I would not say a lot. There was a few works over the years of twisting of oxide. This is a calculation from Longqing Chen, and what they did here, they took two bilayer of CFO, rotate them at a certain angle, put them on top of PMMPT, and strain the PMMPT. And what they've seen in the paper is that they could go from parallel magnetization. When they apply field, they're going to anti-parallel magnetization. They remove the field, the magnetization changes anti-parallel, and then they apply field again as going back to the initial state. So it's basically non-volatile way of doing this. I haven't figured out, to be honest, in the paper, maybe I haven't read it carefully. I haven't figured out whether it was also experimentally. For sure, it was a simulation. But whether they confirm it experimentally, I haven't figured out, so I would not say. But this is the experimental observation that they've seen some relation due to the twisted material. So there is effect of twisting. We know also there is something about how the twist of membranes can bring about some properties. This is the work of Jacobo, and I don't think I will say more than what he says because you have seen it before. So here you can put 2 layers of barium titanate, rotate them, and you can see some vortex, which a ferroelectric vortex. I don't know what to say more because I think most of you have seen it before and heard the talk of Jacobo, but this is another experiment where in my opinion, it's the first experiments where someone took the 2-layer and see this effect at the interface where we can see some influence of the rotation at the interface. There was a following paper on top of this paper, and I think Leni was mentioning, someone asked about, yes.
I have a question on the slide. But these figures, not this one, the one before.
Yeah, let me go back, yes.
These magnetic or electric figures can be transported in this material? Or you just can be transport? Like, I mean, like skyrmions, can transport skyrmions. I mean, because you know, every time you show a lot of these images which are static, no?
Yeah.
But I mean, for
I don't know. I don't know, and I don't think Jacobo testing it as to move it, but I don't know.
I was just curious because I don't know nothing about that. So
I don't know if you can move them.
I don't know, maybe applying a magnetic field or a potential, electric potential. So
I can see your point. I mean, if you have some other feature, you can maybe. I don't know. I don't know whether you can move this feature. I don't know. I cannot answer. So there was a follow-up paper recently from Science Advance, and I was about to say that Leni was mentioning. Someone asked about the flat bands. Okay, but this is okay. So this is a theory paper from Minnesota, and they just follow up what Jacobo did, and they did some calculation. And I'm not going to go through all the theory of this because I don't know in detail all the theory. What I know that the conclusion of their paper is that they have a twist angle, magic twist angle, which they claim it's 90 degrees. So, and 90 degrees, I think it's not what Jacobo did. So maybe the people can go and test this model. But the model fits very well with the result of Jacobo, which is good. I think it's just confirmation that the work was done correctly and can repeat it at least with a model. Although the twist angle is different. The magic angle where they said that the polarization is the highest is in 90 degrees and not in the angle that Jacobo was looking at. We did some calculation and work earlier. Also, we looked at the trace diffusion coefficient of oxygen as a function of twist angle. So what the idea here is you take 2 strontium titanate and you rotate them to different degrees. And we looked about how easy or how difficult is it for oxygen to move from one side to the other side. Basically, it's a diffusion coefficient traced of oxygen. And we found out that there is an angle dependent here. So you can see that the angle dependent, unfortunately, is going the opposite way. So it's become worse when you twist it. But this is just one material, and you need to think about some other material. I mean, our idea is to take some other ionic conductor material, try to twist them, try to find the right condition where we can enhance the ionic conductivity of the material. But this is just motivation for some people. And another thing that I want to motivate here is that so far what I showed you is the 2 crystals which are similar. So BTO and BTO, SFO and SFO, STO and STO. What if you take 2 crystal structure with a different symmetry and put them together? What will be the result? And so you will get a different moire structure here. And the properties is still, of course, unknown because we didn't do it, at least for the oxide. What we did for the oxide and what was recently shown by the group of Hwang is that they did some simulation, and the simulation show also, so if you take square and hexagonal, you'll get also this moire potential which go in a certain direction. We did some experiments where we showed that if you take the STO and the cerium gadolinium oxide, you get something resemble what we see there. More than that, we haven't looked at the properties, but it's important to open up the thought that you don't need only to take two crystal equally, but you can mix crystal also and get different results. Okay, that brings me to almost the end of my talk, and I want to bring here a question to you. So this is a paper or someone, I don't remember the authors, but it was published in 23, and it was a Pryds work. You can see people took 2D material and start from 0 to 2 to 4 to 6 to 8 and did that work. I mean, if you have to do it, if I have to do it in my group, in my place, I think it would take forever. And I don't think I can repeat this one because it's impossible. That was my point to begin with. It's okay for this paper, but I cannot go and repeat and do the 90-degree or the 20 or the 2-degree, not because I cannot maybe get the 90-degree. I can get the 90-degree, but we have maybe the material are different. Maybe the cleanliness of the material is different. There is a few questions that one may ask. If you observe any new phenomena, we have to think about, can we repeat it? Or is it something that we saw and that's all, that's a Nature paper. We need to think about how can people also repeat and do the same experiments out of it. So the question is, can we, and I think Leni was started to talk about it in the end of the talk, and I will continue now in my talk, and I will end with this. Can we continuously twist a membrane? Can we take a membrane, two membranes together, can we put them together, continuously twist them, and then watch how do they behave while we're twisting them together? What is the advantage? Advantage that we are not using different material. We're using the same material and twisting it continuously. And another advantage, once we are cleaning or do the things, it's the same material, basically. We can compare the same material, the development at the same material. So this is what we are currently building together with Shachar Ilani from the Weizmann Institute. He developed it for 2D material, and we are now modifying it and building it for the oxides. So we're trying to do, and there is a few challenges with the oxide. 2D materials, I will not say it's easy because it's difficult to make it also to put everything together, but for oxide, it's even more difficult. So what we are trying to do here is that, I think what Leni showed before is that you have the microscope. Basically, it's an STM. It's a two-dimensional STM. You can think about it. In normal STM, you have a tip, and then you resolve the energy and the momentum at one point. Here, in this device, you can resolve the energy and momentum of an area of this. So if you are able to make two layers which are parallel to each other and clean, and there is no defects, and they are conductive, and everything is like we want, then we can get a coherent tunneling, and then we can image directly, and then we can get two-dimensional. That's what they did with the beautiful picture. That's what we want to do, and we are currently building it in my place together with Shachar. And in this work, Jacobo and Mar Garcia is also involved, and some other people also involved in this work. So, like I said, we're rotating it, and what we can get out of this, the whole idea is we can get the bend we can get the whole structure at the same time while we follow it. And now you don't get the phase diagram, of course. This is just for illustration. You get the bands, and for the bands you can get the properties. So you can reconstruct everything, and I think it's a very powerful technique that hints both the model people, because we can provide the band structure back to the modeling people, so they can maybe predict some other phenomena that we have not seen or we cannot see in the microscope. One of the things that we are thinking of in the future is to add some stimuli into it, for example, light or temperature, magnetic field. So it's really open to many applications. And again, I just want to emphasize, this is not our development. It was developed in the Weizmann. We are just in agreement with them. We are building it in our place. But I think it will be the first time that such a microscope is built somewhere in the world for oxides. So, okay, now we build a microscope, and can we also keep it clean? And this is obvious. So we are going to put it inside the system. So we have a unified system where we can make the material in a closed system. We can twist it, we can test it, everything in a closed atmosphere. Again, in order to reduce the chances that the interfaces are not clean. We need, and this is one of the things that we can do. There is many other things, but this is one of the things that we can do, and we have this advantage that everything is in a closed system. So with this, I would like to end up by having some take-home message, and I hope again to motivate the people here. There is a few things that we need to achieve. Is we must ensure a precise control over the cleanliness of the interface. This, I think, everyone should try to do it in his or her own way, and maybe we can share information. I think it's important because that's the only way we can move in the field. And then we should develop a reliable method for twisting them accurately and repeatably. So if I'm doing some experiments in my lab in 1 degree, you can do it in your lab in 1 degree, again, with the same thing, at least as close as possible to. The degree should be the same, the cleanliness and the rest of the challenges that we have, we need to assume that we can do the same. Basically, if we do all of this together, if we do all of this, then we can begin to compare some result together, and I'm thinking that will advance, obviously, the field, because I think we are in the early stage. In my opinion, we are in the early stage. We're using a lot of power and manpower to develop the methodology right now. We are, in my opinion, again, on the twisting, we are just babies compared to the 2D material we have developed for many years, but we have the advantage that we have a very interesting material. And with this, I would like to thank you for your attention.
Any comments or questions? Wait a second.
Thank you so much for this informative and inspiring presentation. Just referring to the slide where you mentioned that you have an patent application in the process.
Yeah.
The underlying novelty is more about the software itself, or there's a
the underlying, sorry?
Novelty.
About you want me to tell you? It's a methodology. It is. It's about the methodology. So you need to find a way, and I wish I could say it now, but I cannot, because we've worked about this almost 2 years now, and we want to first prove it, and we want to write it before we going out with this. But the idea is to try to find a way that I can do it in an angle, clean, and then I'm giving it to my fellow who is in my lab and telling him, look, this is the methodology, do it again. And he will do it again, and we can compare it, and we can see the same thing. Whatever you do it, if you can find a way of doing it, that's fine. I mean, there is many ways of doing it. We just find one way that we have done. I'm sure you can find many other ways. So that's my answer to you.
Thank you.
I think we have a couple of questions from the.
Yes.
One is, how strong an electric field is needed to isolate the flat band in ABC trilayer graphene?
Oh, this is a good question.
Okay, sorry. Okay, is the one that okay. And the second one is the dislocation destroying the Moire pattern?
I don't think so. I don't think they destroy the Moire pattern. I think the Moire pattern is part of the, not part of this as a Moire pattern, but it is underneath the Moire structure. This is my feeling.
Other questions?
So my question regards this new development and quantum tunneling.
Yeah.
So how are the tips? Let's say you mentioned
Yes.
this.
Yeah.
Which is the size of the area?
Yes, yes. The stage that we are working on, where are we now? So the challenge in this is to make two flats and clean surfaces that come together. And the challenge with the oxide is to make oxide which conform a tip. Now it's not a FM tip. It's a truncated, for example, pyramid, as you saw in.
But the size of the area.
It's 2 by 2 micrometer. The size of the truncated, so it's small.
It is small, but
small.
You need to be coherent.
Yes. Yeah. Of course, you need to make sure that it's clean.
So it's 2 microns, more or less.
It's 2 micron by 2 micron, and it's have to be clean at this area where it is. Yeah. It have to be clean. It have to be flat. It have to be. So how to make it flat and how to do this? There is different ways of doing it. Some of this reported in the paper, and some of this we have to try to do. So we are working on it, and I have two people working on it the past 2 years also now, 1.5 years at least. So it is a process because it's not trivial, because you need to find the right condition, thickness, material that you want to do. They have to be conductive. They have to conform good. Some of them break when you put them on the tip of something. Although what I showed yesterday, it's conformed really good. And then you say, okay, why does it break here and not break here? It's break because of the shape of what we did there. And it's break because you put something that we discussed a little bit yesterday. If you have a material, you don't want it to fold on each other. You don't want it to fold on each other. So you need to find a way not to let it fold, because once it folds, it can initiate cracks. At least we see.
Okay. Thank you.
We have another question from the Zoom, from the same person. For the continuous twisting, why 2 membranes are needed? And could it be between one membrane and one substrate? I mean, the Moire pattern. I guess yes. No?
I'm not so sure what I need. Why 2 membranes are needed?
He's saying you have 2 membranes and you are trying to.
In principle, you can have a flat substrate on top.
So the answer is yes.
The answer is yes, of course, because what you need 2 surfaces basically, and you need to tunnel through the surfaces. But we are interested in the membranes itself. So we're interested in the properties of the membrane, not of the. You can do it with the crystals.
Okay. Other questions or comments?
What is the cleaning procedure you are using?
Clean?
Yeah, the cleaning. I mean, it's like an oxygen plasma or? Yeah,
so the normal procedure that we are doing to clean it when we're doing a single layer is plasma etching, heating it up to a certain temperature, depending on the material, whether it can tolerate under reduced atmosphere, and then protecting it, taking it to the etching. Plasma etching on a different condition. And I must say that there is challenge there, because we have seen, and we still see, but we are optimizing it. And I think many of the people working in the group, like Raesh, is also looking at it. There is a residual of polymers always. And even if we don't see it by X-ray, or even if we don't see it by eyes, we can see it by measurements. When we try to measure the electrical conductivity of this, we can see some response that is not correspond to if it was normal material. So what we do is we're cleaning it, and then we're testing it now as almost rule. We're trying to do it with Raman and XPS to see that there is no traces of polymers on the surface. So if there is something, we take it back and etch it, and then going back, because we need to remove all of this, and then you need to protect it, of course. So you need to put it in a place, and you need to move it in a locked system, so it's not. It is important, I mean, because once you're doing good sample, then you can use it to many good experiments. But if you do a bad samples, you can spend a lot of months and seeing something which is not reasonable.
I have a question about back to the quantum tunnel microscopy. I don't understand how it will work. So with the tip, you will need to land on one membrane, and then you will have the other membrane on the holder, and then you will put them in contact to each other, but not so much that it will fix this angle, and then you tunnel between the two. Okay, and this should be done in situ. So potentially you will need to deposit one of the membrane which you want to check the twist on top of the truncated bipyramid.
We need to put not deposit, but we need to transfer it.
To be able to transfer it.
Yeah, that's what we're doing. That's what we're doing. And one thing I didn't mention, but when you put the two layers on top of each other, we often put HBN. We want to put HBN in between because
that was the second question. How do you avoid the ionic?
So HBN in between. HBN help both lubricating the surface. We were just talking about this morning. It's helping to lubricate because it reduces the forces, and then it's keeping it away so we don't touch the material. So it's keep a distance.
Do you think that the HBN then it's a way to get rid of the ionic forces between the two membranes? Uses a strategy?
I think it's not to get rid of, it's to reduce. Because I don't think you can get rid of. I think what we think, and we have to test it. So all of what I'm saying now, it's fission. So we have to test all of what I'm saying. So we believe that a membrane, or we thought about HBN, to put it will behave like a lubricant. It will reduce the forces and will be. In fact, we did some simulation, DFT simulation, not some other people in the group, and I was again mentioning this morning that show indication that you put 2D material graphene on top of oxide, it's slide quite easily. And that was also support what we think, we hope, is that it will help us to rotate it without having other forces that we don't know. So we have to test it. And if one layer will not help, we put 2 layers or 3 layers or 4 layers. We need to find a way to compensate for any strong bonding that will not enable us to rotate it.
Thank you, Nini, for this inspiring presentation. We have seen that in graphene, the Venn diagram depends on the interspacing between the 2 layers.
Exactly.
So how are you going to differentiate this effect in this microscope? Because if the Venn diagram depends on the distance between the two layers, the interface between the 2 layers changes the Venn diagram. So how are you going to differentiate this effect in the microscope?
Yeah, so therefore, as a starting point, we want to use HBN. And so we think it's inert, it's insulator, so we don't involve any graphene at this point, anything. We want just to measure a tunneling current to begin with. We want to see that we can twist it, and we want to see a diagram which show a rotation as a function of gate, for example. This is what we want to start with. Later on, we can think about other interaction, like you say, true. I mean, what happens if you put a graphene, or 1 layer of graphene? So the more internally will also maybe influence. We don't know. In fact, this is a way of testing it. So
yeah, but I mean, the distance between the 2 monolayers, do you think will influence the Venn diagram and the conductivity?
The distance when you put a different layer?
Yeah, between the top layer with the cantilever and the bottom one.
I think at a certain time, the certain distance it will influence, but I don't know what are the distances that will influence. So we have to test. That's what we are going to test together with Jacobo. And so we try with 1 layer, 2 layers, 3 layers, and then see what is the critical place where you begin to influence the. But I think we are 1 step back when we don't even use the graphene. We use inert material just to see that it's working, first of all, because this by itself is a challenge.
Thank you.
Other questions? Okay, so if not, we can thank the speaker again. So we have now half an hour of coffee break, and so see you later.
Hello, everyone. Welcome back. I'm Carla Mena. I'm a PhD student here in ICMAB. And let me introduce the last talk of these 2 days. Would be from Leni Bascones. So the floor is yours.
Okay, so thank you. Thanks again for being here now, also in this second talk. So now I'm going to talk now about a bit in which way people is looking to this system from a theoretical perspective. Okay, so somehow we have these mores, and here there are several things we will have to focus, we will have to care. So of course we have this more pattern. So one thing is it's a bit on the lattice. The key ingredient from which we start is, as I said before, is the existence of these flat bands. And then, so of course, well, of course, at least from my point of view, that I look at correlated systems. So we care and we want to understand these correlated states. Okay, so we have different type of system as compared to the standard bulk materials. So people is using different methods. Of course, there is some, depending on which method is going to be more or less interesting, depending what you are looking at. So something that it's standard in materials. So if you want to get the bands or you want to get the structure, normally people is doing ab initio calculation. But I will say that here it's a bit different. There are, for getting the bands, atomic like time bending models. People is using a lot continuum models, and I'm also going to talk about effective multi-orbital models for the one. For the correlated systems, there are all the techniques that, in principle, one is using in other systems are also used, and of course, one can calculate many things. Okay, so let's start. So the standard way in which people look at the bands, or the first bands that one gets, so it's doing some type of ab initio calculations. In this way, one gets the lattice structure and the bands. What happens here? Here, what we have seen is that when we rotate the layers and we have these more patterns, we have a larger unit cell. So this unit cell can be large and large. And as I said before, for 1 degree is of the order of 10,000 atoms or larger. So it's larger. So that means that, well, your calculation can have some trouble. So it becomes really big calculations. You can imagine how many theory papers are on twist bilayer graphene, and in particular magic angle twist bilayer graphene. I think I have seen one paper in which they do ab initio calculations for the magic angle. Okay, so this is normally done if you have smaller unit cells. So it seems that it's possible because, as I say, I have seen it with one paper, and maybe there is some other, but not much. Well, of course, the good thing is that you get the atomic positions. And well, one thing is that you are, in that case, you are restricted to commensurate structures that normally in other situations, even that can be released. So another possibility that one could think on is to say, okay, maybe if we know, like from from having 2 layers, how is going to be the tunneling between the 2 layers, one can do some type of atomic like type bending model, is to say, okay, we put all our lattice and we put the tunneling between the atoms, and try to get the structure from there. So this is somehow less consuming, and there is some people doing that. So again, in any case, your unit cell is very large. And and in fact, what is really controlling your behavior is all this Moire unit cell. Something that people is doing a lot in these Moire heterostructures is using continuum models. Continuum models and you lose a bit information on the atomic distance. So normally it's something that you play with the system, whether in K-space, whether in real space, assuming it's continuum in the sense that you don't care of this discretization between the sublattices. You have the graphene sublattices, but you lose a bit the discretization. Let me give you an idea of how this is done. In particular, so this famous picture from the magic angle, it was done using a continuous model. So when it was studied. So the idea here that people does for getting the bands is to say, okay, so this is one of the graphene layers and the other graphene layer. Okay, and so I'm going to see how they mix. Well, graphene or other material, the one that corresponds. So normally you build your kinetic energy. So you are Hamiltonian having one layer at K. So and here normally you are already in the dispersion in K space. Okay, in momentum space of one of the layers that later I will show for graphene is the Dirac. And normally you are going to be interested in what happens only at low energy. So you don't need to know. So in graphene, you have dispersion in a range of electron volts, but you normally are only going to be interested in what happens very, very close to the Fermi level, because at the end of the day is what is going to control. So you put one layer at K, dispersion, as I say, in K, and another one, well, at K with rotation, which is theta over 2, and another at K minus theta over 2. And then you put how the two layers are going to mix. Let me give you some idea. For example, for graphene, here what we are going to be interested is in the fact that we have some Dirac. We have this linear dispersion. Okay, it's not that we need all the details of the graphene. So what we need is to put here in our system just, well, here we put the two sublattices and some, so the way in which these two sublattices see each other to give these Diracs. So you put it here, and for the tunneling, normally some approximation is done. So for example, an approximation that is many times done is to say, okay, so these two layers see each other mostly here at the center of the Moire unit cell, because there you have atom on top of atom in this A stacking. And here at the edge, at the vertex, you have this other stacking, which is or AB or BA, in the sense that you also have some atom on top of atom, but in a different stacking. So you assume that it's these two, so these are the processes that are really going to give the coupling. Of course, you can complicate this more and you can be more elaborate, but this is already an approximation that is very, very much used. So in the case, for example, of the chalcoionides, here we will, even our unit cell will contain 3 layers, but you don't need so much. So normally what is done is, well, people here just, what people is doing is looking only at how is the top of the valence band, because it's the one that people is doping. And so what you have is, well, so in general, this is KP approximation is some type of parabolic band in which it comes, it's coming mostly from the this transition metal atom. So, and then you approximate this by this, is what I say, by this parabolic band here. And also here, if you have two different materials, well, these two, the dispersion here, it will be different. Okay. Now, you have to consider also which is the degeneracy of your system. Like, for example, if you have more than one valley, you will have that degeneracy in your system. So here, as I mentioned before, is that so in each of these bands, they are not spin degenerate. Okay, so here it's only one of the spins is going to be included in the model normally. So, and then what is going to be key here is that depending, before I told you that you can do this AA or AB stacking. So if you have the AA stacking, if you put one on top of the other, so they will see each other with the same spin. But if you have AB stacking, the spins that you put in when you put one atom on top of the other, it will be opposite. Okay, so then if your layers are just parallel perfect, you will have no tunneling, and the layers will be decoupled. Now later we are going to see that the layers are not perfect. Okay, so this is the type of things that the type of ingredients that you include. Okay, this should not be here. No, okay, yeah, this should be here, yeah. So this is one way to get the bands. Now, for many, for understanding many things, once we have the band, we probably, instead of trying to work with all the atoms in our system, or trying to work in K-space, so we may want to do some type of multi-orbital model similar to the systems, so to the descriptions that we do in standard bulk materials. So, for example, in a standard bulk material in which we have an atomic an honeycomb lattice, we could say, okay, we just have kind of moire atom, very large, okay? Or so the question is, and so for many for understanding many things, this type of models is particularly useful, and also for many techniques. So can we build these models? Well, so here there is how are these models depends a lot on the specific system, and in particular, what is going to enter into the game is how is the topology of the bands that we have. So, for example, this is and one thing is that it's going to be different for magic and gold graphene and other systems. So here we start from bands in which has been calculated in some other way, normally from the continuum model. And what we try to do is to fit that bands. Okay. So for example, imagine here this is this ABC trilayer graphene, which is a line of boron nitride. We saw this has these flat bands, and it folds with the boron nitride. Before, some people ask how large has to be this displacement field to isolate the bands. So normally, well, later we can check the displacement experimental one in terms of the energy, the voltage drop is normally considered of the order of 20, 30 milli-electron volts. But later we can check in one of the pictures how large is the D that you put. Okay, so in this case, it's interesting. This band, for example, one of the bands is trivial in the topological sense. So it's similar to what one will have in just a single orbital model, if we just have a normal lattice. The other one is topological. So if we just look at the band that is trivial, we have a valley degeneracy, so we have two bands. So one can really model this system in terms of just a triangular lattice in which we have this very big atom, which is at the center of our unit cell. This is also a bit the idea that I mentioned before. And you get, well, this is plot in different directions, but you get these bands, and you can work with this for you to make your models that you are going, or your understanding. Okay. Now, the case of twist value graphene is a bit more complex. One thing, important thing for getting the physics is later to think whether this band is isolated. So how many bands you have to consider can be also dependent on how large is your interaction. Because if your interaction is much larger than the gaps, that if you neglect these bands, maybe you neglect part of the physics. But in principle, it's doable that you do that. Now, in twist value graphene, the first thing that people tried to do was just to fit these flat bands. So these are these flat bands, okay? We have here what you see is for the two valleys, for the K and original K and K prime point of the graphene. So, okay, we have two conduction bands and two valence bands that in each of the valleys, they are separate. They are uncoupled. So the question is, people try to say, okay, can we build a multi-orbital model only for these two flat bands? So, well, people really did some binarization and got this. You will say, well, it looks great, right? It is not. Well, in fact, something interesting here is that, well, here, when you look at the charge, where is the charge? So mostly the charge is concentrated in the real system at the center of this Moire unit cell, similar to here. Okay, here is, one thing is that here, these orbitals that I have put, this triangular lattice, is centered at the same place where the charge accumulates. So here in these two layers, the charge of these flat bands is not homogeneous in the Moire unit cell. So it's kind of concentrated mostly in the at the center of the unit cell. So here the problem, and here, interesting, when they tried to build this model, it was interesting because the lattice that they had to consider, it was a honeycomb lattice, and the charge was not in the same place where this multi-orbital was centered. Okay, so and the problem here is associated to a topology. If you really try to satisfy the symmetries of your system, you cannot really build these orbitals. So somehow is that these bands are topological, and well, in a topological band cannot be represented just with orbitals which are exponentially localized. This is typical of systems. So in reality, what people have realized later is that if one wants to do one of these models, so there are models that can be done, but one really have to include other bands that are away. So our system becomes much more complex, and our Moire orbitals, in which we treat these unit cells as if they were big atoms. So we are going to have orbitals in different places in the Moire unit cell. There are some orbitals that are going to be particularly important, is that if you see the flat bands here are mostly of one of these colors. It's because we are going to have some orbitals here at this triangular lattice that really give almost all of our spectral weight, all of our bands, but this change here at the center of the Moire unit cell. So I'm not going to go into detail, just have in mind that this type of things, later this will appear again, that this is a very tricky thing that, that really happens, and that will have very important consequences, okay? So our model is a bit something like that. We have some orbitals that give almost our band, except here, and here we have some other type of orbitals. Something I want that you realize is that these orbitals are going to be very flat. So they are going to have very small kinetic energy, but they are coupled to more itinerant electrons. Okay, so before going a bit to the consequences that this has for the description, let me just give you some idea of what happens with the atoms. So far I have been talking about the layers as if they are two they are completely not bended, not modified, like the standard graphene. Okay. Now, in real life, this is a bit more complicated. There is some modulation of the in the unit cell. In particular, I don't have it here. Okay. So in particular, when you put if you put the normal stacking AA, one layer on top of the other, and you compare it with the AB, with this Bernal. So the Bernal, one thing is that it's more stable, and also the distance between the two layers is a bit smaller. So here, this is also happening is when we are at the center of the moire unit cell, so the two layers are a bit farther apart, and when we are here. So they are closer because this AB, so this it's more stable. So then it's a bit buckled the layers. Okay. Another thing that happens is that the atoms also move. Yes. A bit is a bit, not not the buckling that I'm observing here.
I wanted to ask this question before, and since you are introducing now the concept of the distance between the layers, I think it's an appropriate time. At what point, at what distance do two graphene layers become a graphene bilayer? At what point do they start talking to each other, and does this moire concept become relevant?
So the distance I have been, but I somehow I didn't have the connection. Just before the talk, I was trying to, because I said I don't remember exactly. I knew that this question was going to. So these are a few Armstrong. So it's not, but it's like in the standard bilayer. So the distances are normally similar. So here, what is it becomes very important is the angle. The angle, it has to be below 2 degrees is when things start being. But the distance is a few Armstrong.
A few angstroms. So if there is intercalated contamination between the two layers and the distance between the two graphene layers is more than a few angstroms, they stop behaving as a bilayer. Is that?
Yes, at some point it stops. Yeah. So somehow it's because what is key here is how large is the tunneling. Yeah. So it's
basically the distance has to be comparable to the interatomic distance in plane.
Yes, exactly. Okay. Yeah, so they are of the same order of magnitude. It's a bit larger, but they are of the same order of magnitude.
Perfect, thank you.
So another thing that happens here is that, okay, so this, we will imagine if you just put the two layers rotated, so this AA is large and this AB it's small, because these AB regions are more stable. When you when the angle is small, they have the tendency to expand. The atoms move in such a way in which you can see here is instead of having just this generic shape, what you see is that this AA region becomes very small and this AB region become large. So this depends on the angle. Okay, you see here the pattern is how for 2.65, this center of the moire unit cell is more or less as we expect, so it's large, but so later the atoms reorganize and make that this, it's mostly, most of the moire unit cell is associated to these domains of PA, AB stacking, okay? And another thing that happened in plane, this is in plane, okay? This is interplane, this is in plane. Another thing that happened in plane is that there is, the atoms also move, they rotate. They, a bit in this vortex way that we have found, we have seen before. The atoms have the tendency to be displaced in this rotational way. This has been calculated in different ways, both with initial calculations and through some models of continuum models for the elastic energy. Okay, so well, you can see, for example, that how this was the displacement map of the titanium in this twist by layers. So there's, you can't see, so here there is, well, this what you see here is a bit also the way in which it moves. There have these vortices. And so somehow this type of effects are important to observe this this behavior. Another system in which this relaxation is really key is what I was saying before in this transition metal dichalcogenide, that if you put them in this AV configuration, if the layers are not buckled, so we will not expect to have tunneling because there will be a spin up and a spin down, and so it will be forbidden. In reality, because of this buckling, the spin is not in the C direction is not well conserved, and so the two layers see each other. Yeah.
So regarding this last point, just for me to have it clear, if you don't have the spin non-conserved, the model that you have presented so far in the multi-orbital included the spin, or was this a spinless model? It
Okay,
was.
so is that that model was for graphene. This is for the transition metal dichalcogenide. Yeah. In the transition metal dichalcogenide, you have, so that depends. For example, if it's AA, normally you have just AA. Is that okay? So let's.
So you should complement the model Hamiltonian that you showed before with the multi-orbital with the spin component that was not.
So normally, for example, it will be a bit for the dichalcogenide. Is that you can do multi-orbital models. In fact, that's easier for them. But it will be, for example, for one of the layers, it will be somehow up, mostly a spin up, and for the other model, it will be mostly a spin down. There is in reality some spin texture, but in the twist by layer, the spin is degenerate. So it's, you can build the models, and you just have to be careful on all these details when you build the model. That you can do that, and in that case, you will not have in the twist in the transition metal dichalcogenide, you don't have the spin degeneracy. So you only keep one of the bands. And if it's not conserved, what I mean is that you are effective orbital. It's a bit mixed, and all the tunneling is just through the relaxation. Yeah.
We have one question in the chat also, so maybe we can check that first.
Yeah.
G-Dye says, will the interlayer distance change at different twisted angles?
I think that the distance is, well, probably it's a bit, but it's not extremely different. But the buckling, it's going to be somehow different a bit in the sense that, for example. Okay. So for example, here, so because the AV region become very large, so you mostly have the distance associated to the AV region. So then it becomes, and here you mostly have the distance of the AA region, but it's not really, so it's important, but it's not something huge. And you have it. Yeah.
This might be an ignorance, but you had this vorticity, this twist comment.
Yeah,
so do you know what's experimentally is this observed? And in general, is it monodomain in terms of the twist, or are there domains?
Well, there are in twist by layer, so far there is kind of, okay, you say, so there is disorder, which still is not completely controlled. I don't know if they have observed all this in really, or if they have looked at this experimentally. But at this point, the samples have domains, but not just domain for one twist angle. Is that they have, normally when people do an experiment many times, for example, if they go with the STM, let's say, they can pick a region with, you have some some twist angle in some other part of the sample.
Yeah, yeah.
There is even there are even domains of twist angle. That is still some people say that this is really inherent in the case of just of the bilayer, that you cannot avoid that, but in other samples it seems.
If I could quickly follow up then with a conceptual or a theory question. So neglecting disorder, when you discuss like churn states, right, in these sorts of systems, is there an intimate connection to this chirality, or on top of that? Is there a relationship?
So, well, even if you don't put these effects in the atoms, you have the, well, that depends, so probably depends on in each system, because churn state has been observed in different systems. For example, for the twist bilayer graphene, you can have these churn states even if you don't put this vorticity. But for example, if you look at so is that one thing is the atomic vorticity, let's say how the atoms move, and another one is just the electronic one. So at the magic angle, for example, the chirality also changes in the electrons, but you don't need to put the atomic vorticity to get these other churn states. But so normally what happens there is that you have, for example, you break, so you polarize it in terms of the valleys and things like that.
I mean, I understood from what you said regarding this picture that when you put these two layers, one close to the other, there is, and you rotate, there is a small shift in the position of the atoms that you have in one of the layers, no? And I found that quite interesting and surprising to me, because graphite, it melts at 1,000 degrees. That means that the bonding plane is extremely strong. How can it be that you just change 1.1 degree and the distance in plane changes?
Well, I think the main thing is associated with the fact that your stacking is modulated in real space. So somehow you are going from having, let's say, an AA stacking to an AD stacking. And so the system has to adjust. So it's more like, for example, the system has the tendency, for example, you can see here is that if the system, when the angle, for example, is small, this stacking, the AV, it's energetically more favorable. So the system has the tendency to move a bit in a configuration that it's more.
The direction, but the layer should be orders of magnitude smaller than within the.
But what I say is that this movement is not huge, but it's there. And if, for example, you are going to see that not considering that for the case of twist bilayer graphene is not. So this backlink, I'm going to show you now. Well, okay, let's go here.
The displacement is in the range of
less than, so it's, I think probably, maybe I'm going to say wrong, I think it's 0.2 Armstrong, something like that.
0.2 Armstrong?
No, maybe it's too much. Maybe I say it's too much. Huge. No, okay. So, well, it's, I say it's small, but okay. So
it's small that experimentally has never been observed, I would say.
Okay, so I can check that, because in fact I say, okay, people is going to ask me about this, and I didn't remember.
Oh, keep going.
So it's, but for example, you can have here an idea of what happens if you consider the relaxed or the non-relaxed structure. So if just your flat bands are, so if your lattice is not relaxed, you will have here these red lines, okay? If you relax that, you have the black lines. So here, in terms of what it's important, or the most important thing for the correlated states, one thing is that if you don't consider the relaxed structure, you can see here that these red lines, the flat bands, are not isolated from the remote bands. Okay, so this is specifically associated to the backlink of the bands. So, but also there is a bit, it's more particle hole asymmetric, and well, there are other details, but except introducing this, so very often we introduce the effect of relaxation mostly through this through some distance that keeps the I would say that makes that there is a gap, that the bands are isolated. It's not very well understood yet how large is that gap. Well, experimentally, there is particle Hall asymmetry, okay? But somehow you see that you have the flat bands, even if you don't consider that. But I have to check. I know that there are small and not most of the times they are thrown away. But for example, here, what I can tell you is that, okay, it's not true. This has been observed. That, if you are interested, I can tell you, because this fact that you have this very large domain VA and very small AA region, that has been really observed. Now that's in very small angle. And so this really, but this is more than geostacking is mostly the Bernal one. Okay, so well, this is what I was saying is how this gap is normally introduced. Okay, so now the question is, if we go, which in fact is the type of things I'm working in, it's we want to study these correlated states. What can we do? Well, we can do many things. So normally to study the correlated states in bulk materials, even oxides or any other, we have use always a lot of different techniques, so that everything depends on which is the origin of the correlated state that we want to look, whether the system is more correlated or is less correlated. So there are many ways. Now, the important thing here is that we don't throw away. So of course, is that the point is we cannot solve our system, our model in an exact way. So we have to rely on different approximations. So the key thing is that we choose an approximation that is giving us is keeping the key ingredients for the effect and for the system. So let me first give you an idea of, for example, there is one technique. Some of these techniques really require some type of some specific description, some other not. For example, one technique that is used the simplest, let's say, to calculate, for example, broken symmetry states is doing hard prefab. It's just doing midfield. In principle, for example, this technique, you can do it keeping all your atoms. You can do it in a bit different way, just having your bands in K space obtained from this continuum model. You can also do with this multi-orbital system. But for example, imagine imagine you are in graphene. In graphene, the interaction is like it's quite long range. So it's mostly screened by the gates. It's not like an oxide. In oxides, normally you assume that, well, you have a lot of electrons that screen your interaction, and it's very common to assume that you have some interaction when the electrons are only in the same atom, or at most very close atoms. But in graphene, that's not. So for example, some people consider all this huge system with all the atoms. And they say, okay, because it's very complicated, my system, and I have a lot of bands, and the calculation is costs a lot, then what I'm going to do is I'm going to assume that the interaction is just on site. Okay, so this is not a good thing to do. You are keeping all your atoms that in most of the cases are not giving any effect, while you are throwing some part that it's important. So this is the type of thing. Other cases is that, for example, depending on which description you do, so your energies that you involve, interaction energies, can be even of the order of electron volts. For example, if you start with the atoms, with these atoms, your interactions in each atoms are in terms of electron volts. So then this means that you really have to consider a lot of bands and a lot of systems. And so that can make that you also have more troubles to get some accuracy. While, for example, if you do one of these multi-orbital models, So the interactions are also effective. You have to calculate them, but are of the order of 10 milli-electron volts. So somehow it's a bit more control for some things. Now, something is that what people have done a lot in these systems, because there are so many broken symmetry states at low temperature, is people have done a lot of hard-to-fog also because it's easier. Now, when you do hard-to-fog, you get broken symmetry state, but one thing is that your bands are normally well-defined. You have some kind of very well-defined bands. Now, in something that we have learned from decades of studying strongly correlated materials like cuprates, like superconductors, like heavy fermions or organic materials, is that in these systems, so the electrons have the tendency to form local moments, and this really modify a lot, not just broken symmetry state, but really gives a lot of unusual properties. In fact, for example, the most studied case, the most studied, or one of them is the fact that many of these systems are mode insulators, or there is mode physics in them, in terms of, like, for example, imagine a system that we theorize like a lot, and in fact, it describes many materials, like many oxides. It's like, for example, you assume that you have your lattice, and you have one orbital in each lattice, and the electrons repel each other when they are on the same side, and that is because of the this repulsion that is important in the same atom. So if you have your band is half filled, your orbital, if you want to have transport, this process, you need to have two electrons on the same side, and that costs a lot of energy. And so this can produce a metal insulator transition. This is a mode transition. Something important is that your mode insulator does not require symmetry break. You don't need to have any type of ordering. Okay. So the question is this physics important in the system? When Pablo Jarillo discovered this superconducting state, because of the similarity to the cuprates, and because of this half-filling, they started talking about mode. And then later in some systems, people still continue about mode. But when all the topology entered, people just forgot about mode. So the question is, well, one can study this physics, and one can address this physics. And in particular, addressing whether the physics is, of this formation of local moment is important, it's necessary to be sure that we don't confuse effects. Some people say, okay, if you look at your system in some broken symmetry state, when you see some effect, you don't know if it's coming from the broken symmetry or if your state is already anomalous. Okay, and also, and this, for example, has been discussed a lot in cuprates and in other the other high temperature superconductors. So if you are in your normal state, the one above all the transitions, your system is very anomalous because your electrons are very strongly correlated, then this will make that that this can affect the so which is your superconducting transition temperature, which is your magnetic, or whether you have some tendency to have some magnetic ordering and so on. So you can see a bit how this happens. For example, to study this type of physics, because it's very much a kind of local physics, you really want to use this type of multi-orbital systems. And so, well, if you have this tri-layer that I told you before, and you have this triangular lattice, you can really study what happens when you introduce interactions. And what you see, this is what happens to your band, is, well, you have, this is your non-interactive band, so your effective band, you put the interactions, and what you see is that you are sending a lot of spectral weight to higher energies. Your band is quite destroyed, and these are the Hubbard bands that has been studied a lot in the oxides. And well, if U is quite large, so you get an insulator. Okay. Now, this is a bit the type of picture that one has studied in many oxides with more or with less orbitals. Now, twist bilayer graphene, it's I told before that it's a very interesting system in terms of how you have to describe these bands. In fact, so this system, we have these very flat orbitals which are coupled, which are going to have this tendency to be very localized, and they have the tendency to be mod, and but they are coupled to this more itinerant system. More itinerant electrons. So in bulk materials, there are some compounds that has been studied a lot in the world of strongly correlated materials, in which there is something related, which are the heavy fermions. Okay, so in the heavy fermions, you have local orbitals coupled to itinerant orbitals. In this system, the coupling is very, very peculiar, because it's only here at gamma, so it's topological. And what it makes is that when you really introduce interactions, one important thing is that to see this physics, you really need to have some very specific techniques. Most of the techniques don't see that. But if you study how the spectral weight reorganize, what you see is that this was your non-interactive band, and this is what it gives. So what you can see as the difference compared to the one before is that here there is no gap. There is very strong differences. So this can look difficult to see, but for example, when you look at the, well, there are different effects, but when you go to see how the density of states depends on doping, what you get is something like this. And this physics has been seen before, has been seen in twist bilayer graphene. Particular is what has been called the cascades. And so this is an STM system, and well, it's really the state which is the most resilient in twist bilayer graphene, the one that remains to the highest temperatures. And really, what it's telling us is that the normal state of our system is very, very unconventional. Okay, so just the summary, there is a bunch of techniques that can be used to study these modern materials. Of course, it depends what you want to study, but just keep in mind that well, the states are complex. Thank you.
Thank you very much. So now we are open for questions.
Thank you for this really interesting talk. I don't know if I missed it, or if you only do this at for relaxed structures. Do you consider dynamics?
Well, so this so far. Okay, so if we want to, we are not in the dynamics, but for example, in principle, you can introduce the relaxed structure in the underlying bands. Mm-hmm. But is that not really see the dynamics, just considering that if your lattice has relaxed, your bands are a bit different.
Yeah.
And that you can include in the model. And then so it's not going to be so for example, it's going to give things like, let's say, it's going to influence at which distance it's this line appear, or it's going to give some particle Hall asymmetry. So it's giving effects, but the big description it will not change.
So in a sense, you introduce some form of electronic coupling, electron phonon coupling in your Hamiltonian, or?
Okay, no. So here this is a static. This is a static lattice. This is what I say. So the dynamics is not included. It's a static. Yeah.
And do you?
Because here we assume that the electrons see the structure but are not so modifying that.
But do you think that could change the shape of the bands, especially in two weakly coupled systems, two graphene layers, where you have in some regions where the orbital of the states, especially this AB region, the atoms are closer to each other. You'll probably have a local electronic coupling that is higher. And if it moves, your electron-phonon coupling is really, really sensitive to dynamics.
So, well, and here, in fact, the phonons are also interesting. I haven't worked on the phonons, but the phonons are quite interesting. But for example, so it's what I say, not considering any relaxation at all, it will be these red lines. So normally what is done is considering that there is this gap opening. So the main thing that is observed, I cannot tell you that for the big picture, the phonons are not doing anything, but I think that the energies here that are involved are quite large. So I think that's
okay.
For some other effects, like for example, is that people is thinking on what the phonons are doing for the superconductivity, and they also think that they can be a bit coupled to the interaction. So somehow dressing some effects, some vertices and things like that.
Okay, I might want to catch up with you later, but I don't want to go overboard with the questions. Thank you.
Hi. So as well as the rotational degree of freedom, there's a translational degree of freedom between the two layers. And it seems to me that implicit in almost all the pictures that I've seen, both from you and from the experiments, there's an assumption that the center of rotation will go through the exact same center of the unit cell for both layers. So that there's always the same AA atom on top of each other, at least, at some point. So my question is, does it matter if they are not? And how, if it does matter, how do we experimentally ensure that indeed, there's always an A atom on top of an A atom when you start the rotation?
Okay, so so normally that is, you say if the center of the unit cell, it's some AA stacking, which is not just one on top of one, but one.
There is a slight shift between the A atom at the top layer and the A atom at the bottom layer.
So yeah. I think it's slightly well, I think that probably the center is more or less fixed, probably even associated to the symmetry. I'm not really sure, but for example, if not, something that you will have is some disorder, but in principle, so normally it's considered that is one layer at the center of the unit cell is one layer on top of another layer, but in reality is that as soon as you start having this displacement, there is it's always shifted a bit already from the beginning.
You rotate, all the other atoms will shift from their relative positions, but the axis of rotation in your simulations, I think, and in
well, these are not my simulations. My simulations are the ones at the end.
In all the simulations that I've seen, and in fact, in all the pictorial representations that I've seen of Moiré twistronics, the axis of rotation really goes through two atoms that are perfectly vertically aligned. And
you say that you have this AA stacking.
Does this translational phase difference make a big difference? Does it not? And that's a question for the theoreticians. And I guess the question for the experimentalists is maybe it does happen because it's a minimum energy that the center of rotation will want to align anyway. So maybe my question
But yeah, so somehow is that the center is not one atom, but is one hexagon, and is the center of the hexagon.
Okay, so what if the center of rotation is the center of the hexagon is not in the center of the hexagon for the top layer?
I think that this is in the so the centers, I think this is, at least this is always believed to be like that, associated a bit, I think, to the symmetry, but the atoms are really probably not one really on top of another one. So the two, let's say the two hexagons are a bit rotated. But I think that the center it's believed to be that one. If not, but one thing that it happens.
It is believed to be, but do we know that it?
Well, at least, so for example, in these simulations that people has looked at, I think that for what refers to the real center of rotation, I think that that's believed to be that one. they always the same one. But another thing, I don't know if, okay, I don't know if this is maybe what you say. What you say is this displacement.
Yes.
That in twist by layer, that does not matter. In other system, it matters. But in twist by layer, you can shift them and it does not matter.
Okay.
But for example, in the tri-layer with two angles, it matters. People really studied that even before this boom of twistronics, that somehow the way in which you map to the system is the same one. Yeah.
Why does it not matter?
I haven't worked on that, but there is some mapping that they really saw that this the band structure does not change. But that depends on the specific. Structure. For example, is what I say. If you in the dichalcogenide, it's very different if you rotate with respect to AA or you shift and you rotate with respect to AV, or even in some other graphene structures. Yeah.
Thank you.
Let me read one question in the chat. Hugo Aramberry says, very interesting, thank you. Is it possible to use artificial intelligence approaches to model the electronic destruction of motifs?
I know that some people is doing that. I have seen some papers, so I haven't seen too many, but I have seen some paper, in particular by Stephen Carr, in which they were, say, like looking, so which type of motif structure could have the tendency to give flat bands and something like that. And also now, well, people is doing some high throughput calculation things. Well, I don't know if this is also to identify which materials you can use for having this type of structures.
So maybe one or two questions? No more questions in the chat. Okay, if there's no more questions, then we will close this talk and we can have the closure.
Okay, thank you very much to all the lecturers that contributed to this school. The school is not over yet, so we have lunch and then the poster session where we again have cookies and coffee and more things. So let me remind that after the poster session, leave the badge here in the box outside the conference room. We can give you a small update regarding the next school that will take place, hopefully this year. It will be on advanced electron microscopy for the STEM and IELTS, and Jaume Gázquez and Roger Guzmán will be the organizers. And well, I would also like to thank the Mulfox group, especially Gervasi, for making this school possible, but also all the other group members, chairs, the people in the registration desk that help somehow make this school possible. So with that, I think we meet at the poster session. Thank you.